Okay, so let us start. So let us recall what we did last time. So last time we talked about tropical curves. To be more precise, we mostly focused in tropical curves inside of P2. So we talked about smoothness. Basically, the underlying graph. Only relevant vertices. We talked about deformation of reducible tropical curve. So that was basically like this. So we described a reducible tropical curve given by product of two equations. So then the corresponding kind of picture was a union of two stars, and then we performed deformations. And one of the deformations, so the deformation is generally non-unique, so there can be multiple deformations. So we can get something like this. They call them this, and then what? Move it like this. So that was one of the deformation, and then this one was smooth, and then this was kind of reducible and non-smooth in the equivalent vertex. So we talked about kind of number of loops and minus. So in particular, we provided kind of tropical geometry proof of this famous formula, the genus for a curve of degree d in P2 is kind of bounded by d minus 1, d minus 2 over 2. Okay, and we also talked about kind of degree of the curve in a sense of curve class. curve graph image. And this so genus of the curve was related to number of loops in a graph with kind of prime example being curve of degree 3 in P2, and then it had one loop. Okay, let me draw kind of reducible curve and then revolve it. Draw something like this, and then to get the curve of genus 1, let us have one more curve, and this graph it kind of has inside one loop, and after the formation, so this kind of figure will be kind of suspended in some way, and that here suspension, so we need to resolve it in 3 points. We resolve it in 3 points, so we will get something like this, and that will give us a smooth tropical curve in a sense that all vertices will be equivalent vertices, and there will be a loop in the graph, and this kind of loop in a tropical graph, it corresponds to kind of handle in the corresponding kind of complex curve. So kind of to recall, how do we get handle from this picture? So we have surface vibration over our graph. So the circle vibration over closed loop in the graph would give us some kind of tori, and here there will be some holes in this tori with kind of other parts of the curve. So that kind of, if we recall the circle sitting on top of each edge of the graph, so then geometrically this thing looks like a tori torus is some tubes attached to have exactly 4 tubes, each corresponding to this one of these 4 edges. Okay, so that's what we did last time. So today we are finally going to talk about formal definition of curves. And we will talk about moduli space of curves. And okay, if time permits, we will also talk about kind of enumerative problems. And corresponding moduli space integral. So definition tropical curve. So we will denote tropical curve as kind of graph gamma with some vector sitting on top of it. So is an equivalence class of consistent decorated graphs. Okay. Yeah, so that kind of structure of our definition. So now to complete the definition, we need to specify like which graphs, how they are decorated, what is the consistency condition for this decoration, and what is the equivalent consistent decoration. Okay, so let us start with this kind of first point, with graph. So we are talking about smooth tropical curve. So it is kind of graph with only equivalent vertices and leaves. So here by leaves we would call semi-infinite edges. So kind of in our examples, so here this kind of yellow curve, which is degree 1 tropical curve, is essentially a graph with a single 3-valent vertex and 3 leaves. So each of these semi-infinite edges, they kind of treat it as a leaf. So we are not kind of assigning 1-valent vertices normally. So we can, and we will do it for some computations, but I think for definition it's just better to call this semi-infinite edges as leaves. Okay, and kind of as we said before, so number of loops is genus of the curve. And kind of number of leaves. Okay, is essentially okay. So to specify curve class, we need to specify leaves with decorations. So kind of either part of, or let's say it kind of maybe better, number of leaves. Okay, so number of loops is kind of a one-to-one correspondence with the genus of the curve, and number of leaves is determined by curve class. And later, when we introduce decorations, we would see how to go between leaves with decorations and curve class. And that kind of general structure, that loops are genus and leaves are kind of related to curve class. So in this case, in this simple situation, we see that this yellow and orange curves, so each of them has 3 leaves, and both of them are degree 1. So this white curve, after we deform it, so now it has 6 leaves, and it's kind of twice as many, so not surprisingly that it is degree 2 curve. And here you can imagine that if I make a reducible curve consisting of d components, so then then this reducible curve would have 3 times d leaves, and after resolution, then after deformation, the number of leaves doesn't change. So in the case of P2, so the total number of leaves is 3 times degree of the curve. Okay. So that is this kind of graph. So we specified what vertices we have, what edges we have. So we have 2 edges, semi-infinite edges that we call leaves, and rest of the edges will be internal. Okay. So maybe I should also specify here. We will also call these leaves sometimes. Okay, in our papers we call them external edges. So let me kind of also introduce this notation that these 3 things mean the same. Leaves, semi-infinite edges, that notation which is usually used in tropical geometry books, and external edges, that kind of notation that we used in our papers. because of some physics terminology that kind of like external particles and internal particles. So these three things mean the same. Okay, so that was our underlying graph. Now decoration. So for decoration, so we have two types of decoration. So we have kind of directions. So each edge of a graph, so edge of a graph connects two vertices. So for each edge and directions or directions for this edge means you choose kind of which we choose the incoming and outgoing or let's say we choose which vertex is beginning and which is end. So in practice, it means the following. So we put an arrow that tells us that this edge goes from vertex V1, so that's the beginning of edge, and goes into vertex V2, which is end of edge. Okay, so and then we put two more decorations. So we have integer vectors. So here, yes, so integer vector f. So for each edge, HE, so each edge means including the semi-infinite edges. So we have vector ME that is integer value, so it takes a value in some n-dimensional edges. So n will be essentially dimension of our target space, complex dimension of our target. So if you look into tropical curve and say is3, so then each of these vectors will be three-dimensional integer value vector. Okay, and then the last decoration is kind of geometric data. Okay, let us call it geometric data because we call it in our paper geometric data. So it is kind of pair of numbers. So once again, for each edge, we have TE and phi E. So we have TE that belong to R plus without zero, compactified by adding zero infinity. So that is length of edge E. So normal kind of edge would have positive length, but to kind of allow for degenerate curves to appear in our moduli spaces, like degenerate or singular curves. So we will include edges of 0 and infinite length. So infinite length, we will need to kind of have this decoration uniform, including semi-infinite edges, which actually have infinite length. So infinite length or semi-infinite length. And the last part of decoration data is phi E, which is on S1, which is T, both and H. So that is just some angle that we assign to our edge. Okay, so then we our decoration. So for each edge we assign direction. Okay, let's kind of do it properly here. Let us assign directions. Okay, outgoing for yellow one, and let's say incoming for orange one. So we are free to do it. Okay, so integer vectors. Okay, so here these integer vectors for these tropical curves would be 0, 1. So here would be -1, -1, and this one 1, 0. So these integer vectors essentially in these examples of tropical curves, so they essentially give us tangent vectors to each of these edges in kind of image of our curves inside of P2. So for this curve, the vectors will be slightly different. So to be precise, will be exactly opposite. So this will be this one. And for geometric data, okay, so here there is not much interest in geometric data because all these edges are semi-infinite edges, so they have kind of infinite lengths, and we don't assign twist to these semi-infinite edges. So twist only assigned to internal edges or edges we find. So after we deform our curve, so then we would have say 3 red edges, and each of these red edges would have some length and twist assigned to it. Okay, so that is part about decoration. So graph decorated. So now consistency. Okay, so there are several requirements for consistency. So first requirement is that integer vector for each external edge or leaf is okay is plus or minus b, where b belongs to the space of primitive normal vectors. So the X is a set of primitive normal vectors for compactifying hyperplanes for X. So we are looking into tropical curve inside some toric variety X. So capital N is dimension. So capital N enters in kind of in dimension of this vector space, this vector sleeve, and then more precise data, which is a choice of compactifying hyperplanes. So that determines which vectors we can assign to external edges. So for now, we say that it can be either b plus b or minus b. Like in our example of degree 1 curve in P2, so this set of so here kind of capital N is 2, so X is 2, capital N is 2 complex dimension, and kind of set of primitive normal vectors for compactifying hyperplanes. So we are kind of choosing them to be primitive normal and inward pointing. So therefore there will be 3 vectors. Okay, so again, okay, I think I will use this notation later. Okay, so let's not just give them. So it will be 1, 0. 0, 1, and minus 1, minus 1. So that is our set, and this set consists of 3 vectors, and for this yellow and orange curve, so for orange curve we assigned all leaves with integer vectors that exactly equal to this primitive normal vectors, and for yellow curve we assigned them all of them to be equal to exactly minus the corresponding primitive normal. Okay, so that one condition. So then there is another familiar condition, is vertex balance condition. So vertex balance condition is the following thing, that for each vertex V, so for each vertex V, we have some kind of, we have 3 edges. Let's call them E1, E2, E3, meeting at V. So all by kind of by definition, all our vertices are trivalent. So there is always 3 edges meeting there, and these 3 edges, they have 3 vectors assigned to them, M1, M2, and M3. So that kind of integer vector decoration. So these 3 edges, they are decorated with M1, M2, and M3. And then what the balance condition is the following condition. So we take a sum over these 3 edges, I from 1 to 3, and here we take a kind of a sum of these 3 vectors with a sign, and we require this to be 0, and this sign is determined in the following way. So plus, if vertex V is nth vertex, and minus if V is limit. So once again, for each edge, we kind of decided by assigning direction to which edge it is kind of incoming. So it means that this edge is end of the vertex, and so here means plus if V is incoming. So let me draw V, and let me draw 3 edges. So say we have E1 directed like this, so such that V is endpoint. Say E2, that is an example. So E2 is directed kind of from vertex V, so it means that vertex V is the beginning of edge E2, and let's say if V also directed in such a way that V is end of vertex. The vertex V is end of edge E3. So then this vertex balance condition in our example would be the following. So we have kind of 2 edges for which V is end edge, is end of the edge. So it means that M1 and M3 will contribute both with a plus sign, and M2 will contribute with a minus sign. And vertex balance condition is that these 3 vectors should add up to 0.
Excuse me.
Yep.
The internal edge maybe still needs the condition 1, right?
You mean this one?
Yeah.
No. So you see, if we start, let's look at this example. So let us look at this red edge. So let us direct it like this, and red edge direct as outward. So then here I know what are the integer vectors assigned to these 2 edges.
1,
So,
0, and 0, 1.
yeah, so it's kind of 1, 0, and 0, 1. and both of these edges, they are kind of incoming for this vertex, and red one is outgoing. So therefore, vertex balance condition will tell us that red vertex. Okay. So in this case, okay. Okay, I need another example. So that was kind of coincidence. Yeah, let me deform this curve in a slightly different way. So I have like two deformations. Let me draw another deformation when I deform it like this. So I deform it like this covalent vertex. So then what do I have? I have something like this, and here this one would, that would be my tropical curve. So that is kind of another valid deformation, and then let me call this now red edge. So for this red edge, so it is a bit harder to compute, but let us kind of orient it like this to simplify our computation. So then vertex balance condition here would tell us that this edge is -1, 0. Then adding this one vertical will give us this red one. If I orient it like this, will be -1, 1. So -1, 1 is not an integer multiple of these three vectors. So that's why the moment you kind of start sort of joining leaves and using vertex balance condition, you can like generate pretty much something very close to arbitrary linear combination of them. So and linear combinations, they clearly not proportional to these vectors. Yes, you will have, so these three vectors, they always form like a basis in V2, so it will be always like linear combination of these three vectors, but it's not necessarily proportional to one another.
And why it could be -b for the external edge?
So that is because okay. So the story is that there will be consistency condition. Just kind of run ahead. So there will be consistency condition which kind of simultaneously flip direction and vector m to -m. So that is sorry, not consistent. Sorry, there will be equivalence relation that will flip simultaneously direction and vector to -vector.
You mean it can all be?
Yeah. So it's like this. So here we have a consistent curve, orange curve. Like all three vectors are kind of incoming, and they add up to 0. But we can imagine, say, flipping here direction. So then these two will kind of be incoming, this outgoing, and that is kind of still a valid tropical curve. So because 1, 0 and 0, 1 add up to 1, 1. And for kind of various computations later, we need an ability to kind of flip directions. So at least for kind of genus 0 curves, that will help us a lot in various computations. So maybe it is possible to somehow fix directions, say to fix directions to be incoming for all external edges. But for various kind of technical reasons, I want to keep this freedom and kind of allow for these vectors to be plus minus b and external edges to be directed both ways, and then kind of impose equivalence relation.
Is that possible? Some edge, some external edge in bx and some in -bx.
Yes. So that is an example. Like here, two edges are in B. So this one equals to first vector, this one equals to second vector, and the third one equals to minus third vector.
Oh,
So I kind of change it here direction. So that is still a kind of valid tropical curve. So it satisfies this consistency. Okay. So now I need to erase. So let me erase this corner. Okay, so now we can. Okay, let me do it the following way. So kind of the rest of our discussion and I think most of our papers so far are kind of focused on genus zero case. So genus zero case is when graphs are trees. So for genus zero case, so there are no more consistency conditions. So this the kind of the third consistency condition. Okay, let's call them A, B, and C. So consistency condition is only for G which is bigger than 0. So let me, since I'm not going to kind of use it, so I will be a bit sloppy about it, and I will just say it basically in words. So the idea is the following. So suppose you have some kind of loop in your graph. So then let's call this the edges in this loop by different colors. So then for each edge in this loop we have the following assignment. So we have direction. Let's assign directions and something like this. So we have direction, we have integer vector, and we have this kind of positive number. Okay, so if you're looking at the smooth curve, so then it's just positive real number. Positive real number assigned to each edge. So now the consistency condition works the following way. So we kind of start with, we say, this vertex V. So then we kind of travel along this loop and return to vertex V. So that is the property. Having a loop means that there is a path on gamma. So for every loop, L is a path gamma on gamma from vertex V belonging to this loop to itself. Okay, and we take this path to be non-trivial. So non-trivial means that we are not looking at a path that kind of starts at V and stays at V. So that would be trivial. So non-trivial path means that we kind of traverse some at least one edge. Okay, so minimal number for smooth curve would be 3 edges, so we transverse at least 3 edges. So then along this path we do the following thing. So we take path gamma. So we have like edges that belong to path gamma. So path gamma is just union of some edges that are kind of connected to each other through vertices. So we take a sum, and here we do the following thing. So here once again we have this integer vectors ME with orientation. So orientation is chosen in the following way. So it is plus if direction of E is along gamma. So path gamma is some kind of directed curve. So we kind of go from one vertex to next vertex and so on. So we have like vertex V where path starts, then the first segment of the path ends at some vector vertex v prime, then it goes to v double prime, and then we have like path induces some orientation. So path induces some direction in which we traverse these edges, but each edge has assigned direction, and this direction may coincide or not coincide with kind of direction in which we traverse this path. So in this situation, the first two edges, their direction coincide with the direction of path, while for third and the fourth edge, we kind of go in direction opposite to, so directions of edges are opposite to direction determined by path. So therefore, first two edges will contribute with the plus sign, and rest of the and the remaining two edges will contribute with a minus sign, and minus other ones. So we have only two options: we either coincide or opposite, and then we multiply this thing by TE, by length of the edge. So essentially, kind of, this thing basically tells us like what is the position of a next point, because if you have TE length of the edge and this ME determines tangent vector to the edge. So that's why here when we start adding these vectors, we essentially determine, so if you add say first two edges, we will determine kind of relative position of this vertex V double prime relative to vertex V. And the idea is that after we traverse the closed loop, the position of this final vertex which coincides with V should better match with kind of position of V itself. So it means that the kind of relative vector between them should be zero. So it means that for each edge, for each closed loop, we impose one linear relation. So, and this linear relation kind of associated to a path gamma. So once again, if you have multiple loops, there are multiple choices of closed paths, but once again, you can choose some kind of basis in this space. So the number of kind of independent conditions, linearly independent conditions, would be exactly one condition per loop. However, as I say, we are not going to use this in our detailed computation, but just for the sake of completeness, that kind of take-home lesson that for each loop, so that's what we would need to get like a full formula for dimension of moduli space. So maybe only in dimension of moduli space we will include kind of number of loops. So for each loop, we additionally impose one vector equation. So vector in a sense of vector in this Vn space. In this dimension. Sorry, not Vn, R. So this length is a real number, so therefore this equation is kind of the sum of a real n-dimensional vectors. So that's kind of the only take-home lesson, because we are not going to talk about enumerative problems of higher genus. So our focus for our course would be genus 0 case.
Excuse me.
Yes.
So here you fix TE as parameters and
yes. So not fix. I assign. You see. So my decoration, I need to assign TE to.
Yeah,
okay. Yeah. Okay. Good point. Sorry, my bad. We have another condition. So this condition we impose for both kind of lengths of edges and twists of edges, because kind of when we assign twist, the twist will also change as we travel along the edge, and we want to return to exactly the same kind of twist as we perform the full loop.
I mean, here it seems ME is the variable in Rn, right? Is the
ME is a variable in Zn, so ME is in Zn. While kind of length and angle, they are in real numbers and in
so
S1.
this capital N is different from those dimensions. This capital N is the number of internal edges.
No. This capital N is the same N as here. So here you see we have like vector equation. So when we multiply ME by a number, we get n-dimensional vector, but now with real components. Because length is real, so that's why we have n real equations for kind of radial part and n S1 valued equations in angular part. Because these angles phi e, they are determined up to kind of shift by say 2 pi. But because vectors are integer valued, so these equations still give us equations in some n-dimensional terms.
So sorry, so this one TE is a vector.
So no, TE is a real number assigned to edge. It's like length of the edge.
Yes, so TE
And-
is a real number. So
Yes.
the number of TE should be the number of
Of edges in a loop. Like the number of TE enters this equation. Like for this case, we have 4 edges in a loop.
Yeah.
It means that there will be like 4 variables in this equation.
But capital N is the dimension of X, right?
Yes. So therefore here there will be like this will be if I look at this equation itself, there will be 4 variables,
Yes.
4 TEs. Like if I assign these m's, that are usually uniquely assigned given balancing condition. So then TE are real variables, and we have 2 equations because we are in 2-dimensional space on 4 variables. So that is fine. This generally has like many solutions, usually like 2-dimensional space of solutions, given that some matrix constructed of this MEs is non-degenerate.
So we have four variables.
4 variables, 2 equations, it means that we will have like 2 moduli. And these 2 moduli is essentially an ability to kind of deform this picture. So that will be one moduli that we can deform like the lengths without changing vectors m. So here, if I just take this edge and parallelly move it parallel to itself in one direction.
Yes, I understand. My question is the notation Rn cross S1n. Those R represent which
So that represents where this vector. So we say that one loop, one vector equation.
Yes.
So one vector equation, vector should live in some vector space.
M, right? Vector
Yes, so
M.
vector is in this Rn space. So vector with n components.
It refers to this ML, ME, right?
Yes, and E lives in z to the power n.
So what's the S1 to the time also?
So S1 is refers to here. So all these spaces, they live in S1.
So it's not belongs to S1 to the power of capital N.
Yes, S1 to the power of capital N.
No, ST is just a number, right? A real number. It's not a vector.
Yeah, but we have this both equations.
So this capital N should refer to the number of edges.
We impose one vector equation. So equation itself is an equality between vectors in some vector space. And
But
this,
we have only one vector, one type of vector, which belongs to R to the power of
and yes,
N. Yeah.
yes. So that's why it's one equation in Rn for each loop. One loop, one equation in Rn.
I think the first equation is in the S1.
Yeah, yes. So one equation in Rn and one equation in S1 to the power n dimensional terms.
We can say phi e as a number module.
Modular to pi shift. Yes,
yeah,
and because these vectors are integer valued, so therefore we can consistently kind of add these 2 pi shifts. They wouldn't affect the equation. That if I take equivalent phi, which is phi shifted by 2 pi, then the sum of these vectors will be also shifted by 2 pi times integer, which is equivalent to 0. So that's why integrality of vectors basically allows us to claim that this equation is well defined on a torus, understood as r to the n quotient by lattice.
But all n dimension, in those all n capital N dimension, we have the same TE.
No, TE assigned for each edge. If you
Yeah,
have
TE
like
give us one equation, right? Each number TE.
no,
Oh.
TE has
Oh,
not
sorry.
each loop gives us
Yeah,
equation.
yeah, yeah.
So say given the same edge may actually participate in two equations. Like you can imagine a picture like this. I don't know. So that is still kind of simpler graph, but just for the sake of illustration, like this internal edge is kind of belongs to two loops. So that's why it will enter to two different linear equations. So there will be like same variable TE corresponding to this edge in the middle, but it will be subject to two linear equations.
Yes, so each edge will give us a vector which belongs to Rn.
No. Each edge has only one number assigned. Okay, two numbers like length and width.
Yes, and will give us one vector ME.
Yes.
So ME belongs to this Rn, which you refer to.
Zn, not
Zn.
Rn, Zn. It is integer varied vector because then this equation wouldn't make sense.
So all three guys, ME, phi e, Te are variables. You solve equations for ME, phi e, Te, right?
ME, as we will see later, they are usually uniquely defined by a curve class. So the moment you specify vectors on leaves and orientation and directions of leaves, vertex balance condition usually uniquely determines ME.
I see. So these two variables you refer
Yeah,
to.
so therefore real variables essentially are T and phi, because M's are subject to some other constraint which is very strong. So therefore this loop equation, this equation for each loop essentially further constrain phi E and TE.
And so we have the same number of Te as, I mean, the number of T's are the number of all the edges.
All internal edges.
Internal
So
edges.
yes.
But this capital N is not the number of internal edges.
Yes.
For this you mean?
So capital N is dimension of ambiguous space. So it's dimension of our target space.
Okay.
So it is true that that you can imagine situations that we have like a very high dimensional ambiguous space and very few edges. So then we may run into trouble of solving this equation.
Okay, what do you mean? I just repeated it.
And that is essentially like that what gives us lower bound on kind of on a genus of the that kind of intrinsically gives us a bound on a genus. The genus of the curve can't be higher than something for low degree curve.
Yes, okay.
So that is something that we haven't proven when we discussed what is the genus of a tropical curve, because I just draw some tropical curve with genus high enough to match with complex geometry computation, but I never kind of proven that in a tropical case I can't produce a tropical curve with genus higher than complex curve. Yeah. And essentially these relations will eliminate this possibility of having a very high genus when we have a low number of internal edges. Because internal edges essentially are, because all vertices are trivalent, so internal edges, and we have like two linear relations between number of internal edges, number of leaves, and number of vertices, and another relation for number of loops and number of vertices, number of edges. So essentially number of loops is determined by number of external edges. So therefore this condition would ensure that that if we try to kind of make a very small number of external edges and still want to have loops, then these conditions would project out a situation that is not possible in complex geometry. So in particular, this condition, let me draw it here. So you can imagine kind of drawing something like degree 2 curve. So that would be, so I draw like two leaves of each type in P2. So that would be like a valid curve class for degree 2 curve, and then I can imagine joining these 3 vertices by some kind of triangle. And then I can think of this as a maybe valid tropical curve whose genus is 1 and degree is 2. So that is something that we don't have in complex geometry. And indeed, if we carefully investigate these additional conditions for this curve, we will see that that here the linear equations for TE does not admit, so for any orientation that you can choose here, so these equations does not admit positive solutions. So these TEs, they are not just real numbers, but they are positive real numbers. So they have this kind of interpretation as a length of the edge. So in this situation there will be no positive solution, and therefore these conditions are kind of important to eliminate this situation that from kind of topological perspective and from vertex balance perspective we can draw, but it wouldn't pass this third consistency condition, which is existence of positive length edges that satisfy this condition. Because here we have a loop, there will be one equation in two-dimensional space, so it will be like one linear equation on two linear equations, like two components of two-dimensional vector for 3 variables, and this equation would have like solutions in real numbers, but wouldn't have solution in positive real numbers when all 3 edges have positive lengths.
If a loop can have 6 edges.
Yeah, loop can have any number of edges. Yeah, 6 edges is fine.
But it can't be 3.
Yeah, so that was kind of minimal that I can draw. So okay, maybe you're right. I can maybe imagine even crazier situation, something like this. So degree 1 curve, like a triangle, kind of suspended inside of other triangle. So I can still kind of find integer vectors for any directions. Like I can solve three equations for integer vectors of internal edges, but I can't solve that now. So only when degree is 3, I will have kind of enough freedom to be able to find like 3 edges is positive lengths.
I'm still confused with the constraint for the twist. Why we don't have a balance condition for twist? No, but so balance condition is for integer vectors. So integer vectors, like when we constructed our tropical curves in examples, so when we constructed a curve in explicit parameterized form. So remember that kind of the change in a radial direction was with the same slope as the change in angular direction. So that was kind of our observation. So therefore for each edge we kind of have a single integer vector assigned to it. So it determines like how we change in the radial direction and we change in angular direction with the same integer vector.
So the balance condition refers to both twist and
balance condition is this one.
yes,
And this one is kind of consistency for each loop. So for each loop we have these equations for both TE and phi E, but usually equation for TE is stronger because phi E can be both positive and negative because it's defined up to
up to 2 pi shift. So therefore this equation at least usually less constrained.
You mean we can choose phi e to any number for genus zero case?
Yeah, you can choose all 3 phi e's to be, say, 0. So all 3 phi e's equal to 0. And then you kind of satisfy this condition just fine.
I mean, why we not write down this condition and here? We only have the M1 plus M2 plus M3.
Yes.
But why we don't have M1 multiply phi 1?
Because we don't need it. So we only need these conditions if we have a loop. So this condition is essentially like having a loop means that there is some kind of circle fiber here, and circle fiber at our edge means that it is some kind of cylinder. So then here the picture is something like a torus.
Yeah, we can.
So for a torus we want kind of radial part of a torus to return to the same point. But we also each cylinder is kind of twisted by phi. So therefore we want this twist to also return to zero twist eventually.
It's like we can glue them together.
Yes, we can glue them together to kind of perfect torus. Okay. Yeah, let me. Okay, I need to read something. Okay, maybe I can fit it in here. Just to have full definition of the work. So the last part is for equivalence relations. Okay. I think I missed one more decoration. Okay, it's good that they have. Okay, but that is still important. So I think I start missing from one. So here we add kind of graph with only 3 round vertices and one kind of specially labeled vertex. So among all 3 round vertices, we choose one and kind of label it as a special vertex. So it's kind of a choice. So then for special vertex, we assign kind of angle in n-dimensional torus and its position on n-dimensional plane. So this kind of position and angular and radial position for a special vertex is not subject to any consistency relations. So it doesn't enter consistency relations, but it will enter equivalence relations. So for equivalence relations, there will be 2 equivalence relations, which is direction flip. So it means that we are doing the following thing. So we flip. Okay, let me draw it pictorially. So we have an edge with a vector m2, and we say that this situation is equivalent to the following situation. So we direct the same edge in a different way. So we flip the direction and we change kind of assign an integer vector to minus itself. Okay, and second consistency relation is that we change specially labeled vertex VC. Okay, so we do the following thing. So we have this specially labeled vertex, and we have phi RC, and then we change it to some vertex VC prime. So we choose a different vertex to call a special vertex, and then we change this labeling in the following way. So we add to phi C kind of. So once again, our graphs are connected. Okay. So connected means that between each pair of vertices there is a path. So then we can travel along this path. So this path gamma is from VC to VC prime. So each path is kind of collection of edges which we traverse. So here we do the following thing. So we sum over all these edges along the path gamma between VC and VC prime. And here we're doing exactly the same thing. So we change this angular position of this special vertex by kind of similar contribution ME with the sign times the twist of corresponding edge. And we do similar thing for radial path. So we just replace like phi by r. And once again, in the case when we have loops, there can be multiple passes. So the path connecting two vertices may be non-unique, and this condition will kind of ensure us that regardless which path we choose, because two different passes between C and C prime will be different by some linear combination of passes along closed loops. And the contribution from each closed loop due to this consistency condition would give us exactly zero. So that's why this transformation is well defined given that this consistency condition satisfies.
I'm still confused with the notation of special vertex.
Yes.
What does mean of special? Which is not special?
So you have like bunch of three valent vertices, and then you kind of declare that this vertex is my special or specially labeled vertex.
You mean we fix?
Yeah, so we choose one vertex and declare that is our special vertex.
And the key point is the length can be negative.
Yeah, so this one is essentially like location of this vertex in the image. So here, like when we describe a tropical curve, we all this data is kind of like internal data, like lengths of some edges and stuff, and this phi C and RC is like position of kind of center of mass of this curve, or overall position of the curve.
Yes.
And to describe it, we choose a specific point, which and kind of curve which is graph gamma gives us natural choices for these specific points is to choose this point as one of the vertices. And then we assign kind of location of this vertex in the image.
Can we select a special point inside the graph, not on vertex? Because it reminds me of initial condition.
No, at this point, no. So at this point, so later when we will have a kind of curves with the market points, then you can you can choose like one of the market points as a special vertex. But for now, without market points, so we choose it as one of the vertices.
Maybe I'm confused with what's the relation between phi e and the vector phi e and the
So phi e is kind of one-dimensional thing. It's always one-dimensional thing. It's like twist and length. While this thing is kind of n-dimensional vector. So phi e is like on the source of the curve, and phi c and rc is on a target, on the image of the curve. So you can imagine like taking abstract graph and kind of mapping it into Rn. So to describe image of the graph, you need to kind of and you presume that image of this graph would consist of union of straight intervals. So then for each interval you need to specify direction at which it goes and length of the interval.
Yes.
So T
So maybe we should change
is the length of the interval.
because phi, we have too many phi's. Maybe the
No, but they should be the same phi, because in this formula they kind of universally join together. Because as you change position of your vertex, you will exactly add some kind of linear combination of phi's assigned to edges that you traverse to go from one vertex to another.
But there are no any relation, right? The vector phi e and the phi e.
Yes, there is no relation. They are completely independent. But we will need this vector phi's to kind of describe properly.
You mean we can choose any vertex to be a special vertex?
Yes. So that's what second equivalence condition is. That you can choose any vertex, and this property just ensures that the overall position of the curve is the same, and you just kind of change it your reference point. Like to determine image of each point, you need roughly image of one reference point, and then you need like a lengths and directions of your edges such that you can determine position of all points by traveling along the edges. And you can choose reference point anywhere you want. So that is second equivalence relation.
But you use T for length, but use R for as a new variable in the target
because T in a sense it kind of lives on kind of on a source space, and R lives on a target space. So R lives on image of the curve, and T lives on the curve itself.
For both image and target.
Okay. This good point. Okay. Now I think in my notes, yes, I used two different files. I used like one calligraphic and one non-calligraphic. So yeah, that is thank you. That is a good point. So I think here I use like non-calligraphic files.
Phi C.
Yeah, for phi C I use like
C means a vertex.
center of mass or something. So at least center of mass, like when you want to give like a position of a solid body, you usually give a position of a center of mass and then some kind of rotation or something. Or if you have solid body, then given a position of a center mass of it, you can determine position of all other points. Because they kind of uniquely all points have like fixed distances. So that's why, as I say, like when we wrote these papers, I was like more physicist than mathematician. So that's why I used physics terminology like external edges instead of leaves and center of mass instead of kind of special vertex. Or there is kind of another word that Andrei likes to use. He calls this data like Rn times Tn torsor data. I'm not sure whether it explains much, but yeah. So basically, like you need to specify position of one of the vertex such that then you can use integer vectors lengths and twist to determine positions of all points on your curve. And equivalence relation tells you that you're free to choose any vertex you want because you can just kind of specify position of any other vertex relative to your chosen vertex by by traveling along the edges that connects two vertices. But kind of in various later computations, we want to kind of keep these two freedoms because we will kind of we will fix these freedoms, like choosing specific directions to simplify our computations, and we will choose sometimes a specific vertex to also simplify computations, and to be able to make these choices, we give a definition as equivalence classes to allow for these choices to be available for our tree. Okay, I think now it's a good point for break. We kind of overdue for break, so now it's 11:11. So okay, let's make 9-minute break to 11:20, and then we will, after the break, talk about kind of counting moduly for
Sorry,
Yes.
I'm still confused. Why do we use this special vertex? In our example, CPQ, we don't see this.
No, in CP2 we already saw this. So you see that in CP2, like when we draw kind of two different tropical curves of degree 1, so these two tropical curves, they kind of have like roughly the same data. So we can like choose orientation to be, say, like this. So they will be like oriented the same. They have the same integer vectors assigned. All edges are leaves, so they are semi-infinite. So all of them have infinite lengths. But in this picture, we clearly see that there are two distinct curves, and the difference between these two curves is kind of position of this trivalent vertex. And that we need to specify this position because it is part of curve moduling. Like if you start with kind of linear equation and complex numbers, there will be some parameters like coefficients of this equation, and these parameters will eventually determine where this trivalent vertex is. So that is kind of an example where this thing is important and shows up in degree 1 tropical curves in P2.
In genus 1 case, if we only change one phi, one twist, a twist of one edge, it's not equivalent.
We change twist on one edge. Yeah, it is not equivalent. Okay, so given that this edge is not part of a loop, because if you change twist for edge that is part of the loop, then you will violate this condition.
I mean, in genus 1 case, there is no this condition, right?
No, the genus 1, we have this condition. Genus equal to number of loops.
Sorry, genus 0.
Genus 0. Yeah, genus 0, yes. Different twists mean different curves. And kind of twists would enter as a variable in the moduli space. So moduli of the curve will be essentially determined by these numbers, by a length and twist assigned to each edge, to each internal edge, each finite length edge, and then the overall position of the curve, or which we determine at the location of some special vertex. So therefore, in degree 2 curve, like for degree 1 curves, there are no internal edges, so there are no kind of twist and lengths. But for, say, degree 2 curve, like this, we have 3 internal edges. So for each of them, we assign length and twist, and we can assign them freely. Like for lengths, it is kind of obvious that if I deform my curve to something like this, that would be a different curve, a different location of this trivalent vertex. So that gives us a moduli which is length of this edge. So we kind of haven't changed any integer vectors or any directions, changed length. And in a similar way, kind of the corresponding twist would also change the curve.
You mean we can deform the twist?
Yes, deform the twist, and that would give us a different curve. So I think like when people study kind of moduli spaces of Riemann surfaces, you can kind of cut your Riemann surface into bands and cylinders, and then you can kind of count the number of moduli by counting like length and twist of the cylinders in a band decomposition.
It's like an automobilism of domain curve.
Okay, that's I don't know. Yeah, sorry. So I know that this length and twist, they are similar to length and twist in kind of Penn's decomposition and constructing moduli space of curves via Penn's decomposition.
I mean, I want to know what does the mean of deform or twist corresponding to the Gromov-Witten?
No, so twist will be like one of the variables in the moduli space of curves. So I think hopefully today we will see like some simple example, like how to define a kind of a form on this moduli space in the simplest case, like counting degree 1 curve passing through 2 points, and we will see like how these twist variables enter the picture.
That means we need to consider the real structure of the module. We change it.
Okay, so I'm not sure what you mean by real structure. So moduli space in our situation will be some. Okay, so in our tropical setting, it's not kind of immediately obvious that it's complex manifold. It will be something like a toric manifold. So moduli space will be toric variety, and this toric variety would have like a radial part or base, and there will be torus vibration. So these R and T variables, they are kind of variables on the base of a torus vibration, and this kind of phi variables will be variables on n-dimensional torus sitting over each point on a base. So that's kind of rough structure of a moduli space, that it is toric variety with and these phi's, they are kind of angular part of this toric variety. So that's probably different from usual thinking of moduli space as kind of complex variety. So here we think of
any complex structure.
Yeah, so we don't at least use any complex structure on it. So we will only use like toric structure.
I'm really curious. Will we investigate the boundary of our moduli to get something like photometric rate? Counting of trees.
So there will be a boundary of a moduli space, and we can even describe it geometrically. And I think in kind of I think that was okay. That's something that I haven't mentioned in introduction. So remember, I said that all this tropical business, it kind of really started when Mikhalkin reproduced this famous 12, which is number of degree 3 curves, degree 3 rational curves passing through 8 points. So he managed to reproduce this 12 by kind of drawing some pictures of, I think in his case it was eight tropical curves, or 8 types of a tropical curves, but one type of the curve comes with multiplicity 4. And then later this result was kind of generalized to showing that these tropical pictures, they contain full WDV equation for P2. So that was how people proven that tropical counting matches counting by Kontsevich and Manin in algebraic geometry. And in that case, they derive a WDV, but I'm not sure. Yeah, I think they derived it, but not by moduli space integral. Yeah, but I think that may be an interesting question to kind of get WDV through integral of a boundary of some moduli space. So I haven't tried it, but that looks very plausible. Because we for sure know that there is some other way of deriving WDV from some combinatorics of these curves, and kind of some combinatorial factors that they got in their derivations. I think they can be understood as probably as some integrals over some strata in degenerate strata of a moduli space.
So the boundary is like the T E becomes infinity, becomes 0.
Yeah, so the boundary would be TE becomes okay, so becomes 0. That is kind of obvious boundary. So that is precisely this situation when you take this edge and kind of shrink it to 0. So that will give you some kind of non-smooth tropical curve that serves as a compactification point for the space of smooth tropical curve. However, I think there would be another strata of a moduli space which is kind of a bit more complicated. I'm not sure that it actually T goes to infinity. Yeah, okay. I'm not sure like whether T goes to infinity is part of moduli space. It's part of a boundary, because in this situation, yeah, maybe we only have boundary at T.
But then T and infinity is like the tropical graph split into 2 parts. Like the red edge.
Not quite. Like for tropical graph split in 2 parts, we can't quite allow it, because splitting in 2 parts means that you kind of cut this internal edge and turn it into 2 leaves.
Yeah.
But for leaves, because we want to kind of curves to be curves with a valid curve class, we want on a leaf the integer vector to be plus or minus one of their normal vectors to compactify and divide them. So that kind of for sure prevents from cutting any edge. So at least the edges which you can kind of cut and turn into 2 leaves, they need to have like integer vector assigned to it to be at least a multiple of one of the compactifying divisors. But even in that situation, I'm still not sure that we wouldn't violate some other property. But at least there is this constraint. Yeah, but
okay, so this question has not been advocated yet.
So I would say the following thing, that we will see probably, I'm not sure, either on the next lecture or lecture after next lecture, some other equivalent way. Okay, so today hopefully we will talk about moduli space integral. So to solve some enumerative problems, we will just use kind of same type of an integral that Kontsevich and Manin used, but instead of moduli space of complex curves, we would use like moduli space of tropical curves. And in that setting, you will have both kind of this angular and radial variables as the variables on your moduli space. So we will integrate over both r's and phi's. However, as we will see, hopefully, okay, maybe at the very end of today's lecture, that phi dependence in most cases is kind of rather trivial. That all these phi integrals, they usually give you something like integer number times 2 pi. So therefore, at least in two-dimensional setting, when you look at a number of curves passing through some points, you can essentially pretend that you don't have these angular variables and instead assign some additional integer numbers to each vertex when you perform, and then just solve a kind of enumerative problem for curves in a radial part, that you have some points in this kind of radial part of your toric variety, and you are looking at kind of a graphs which only have like radial positions and edge length. So in this situation, if you assign a certain multiplicities to each vertex, which are in the literature called Mikhalkin multiplicities, then you will reproduce a kind of complex geometry count. And that is kind of approach that is mainstream in kind of tropical geometry literature. That they really forget about angular part completely. They only think about radial part, but they modify the contribution from each valid curve in a radial part by some integer multiplicity. So these integer multiplicities, they are kind of very easy to construct in two-dimensional case. But generalization away from two dimensions makes the story like horribly complicated. That kind of so that's why most of the progress that people got was the progress in dimension 2, when these multiplicities they are very simple. While in dimension higher than 2, the kind of their approach became like super complicated. So while and therefore they kind of never do proper moduli space integral. And I think we were first in this business who kind of carefully restored angular variables, and instead of using this Mikhalkin's multiplicities, we just kind of performed angular integral and showed that that radial and angular integral can be performed independently, and performing angular integral first gives us precisely a kind of radial integral for a curves of each type multiplied by some integer numbers which coincide with Mikhalkin multiplicity. So that's why most likely people haven't done anything like using moduli space or boundary of a moduli space, because people kind of just drop angular variable in this business. So on one hand, they are correct. This angular variable enter in a very simple way, but unfortunately, it is not generalizable beyond dimension 2. And I'm not sure. Like physicists would naturally say that in dimension 2 we should find an equivalent, maybe more complicated approach with angular variables, which stay the same complexity in higher dimensions. So that's why in dimension 2 you can take a step back to introduce these variables back, and then it's easily generalized. But instead, mathematicians, they kind of follow the standard way in inventing some clever ways of dealing with these multiplicities in higher dimensions. So these ways are clever, but in most cases they are kind of case by case based. That it's some kind of clever invention for P3 or clever invention for P2 cross P1, that there is this and this construction that would allow us to solve like this and this particular problem. While the moduli space integral is universal, applicable to any case, any problem, but yes, in two dimensions, it's kind of looks more complicated than traditional approach. But it is generalizable, and therefore most likely people haven't solved much of the problems like deriving WDVV from this approach with kind of faces or with angular part of this moduli space.
I still have some question.
Okay.
For the WDVV equation, The WDV equation for the general toric target, general than P2, we need some property of the virtual cycle.
It's not what?
Virtual cycle. We need to integrate on the virtual cycle over the moduli space. And this tropical story can avoid this.
I'm not sure that you would have problem with the virtual cycle, because I think WDVV is genus zero property, and I think all this is, first it's genus zero, and second it's not no descendant Gromov-Witten invariance. And as far as my understanding goes, that for a toric variety moduli space for kind of genus zero curves with mark points, they're kind of perfectly fine, and you don't need to do anything virtual. So I think the virtuality appears if either you kind of introduce descendant invariance, introduce psi classes, or you go to higher genus. I think that's the two cases where, for example, you can have a difference between like answer or kind of a signature of virtuality of moduli space is usually when the integrals of a moduli space start giving you like non-integer numbers, because that means that your moduli space was secretly some kind of quotient by some symmetry group. And for a toric variety, this situation is not happening in genus zero no descendant invariance. So all answers are integer numbers. So that I take like as a strong evidence that you don't need any kind of virtuality. However, the moment you introduce descendants, like even on P1, you look at descendant Gromov-Witten invariance, you immediately start getting rational numbers, and that's usually a signature that your moduli space is some kind of quotient with the fixed points, which means that you need to do something fancy with your moduli space. Your moduli space is not a manifold, and I think that's a situation where you want to go to this like virtual classes, virtual cycles. But I think this situation is kind of okay. Let me correct myself for toric Fano. So that's the situation that I focus, because I think for toric Calabi-Yau you can get rational. Okay, so for toric Fano, let me correct myself. So that is a case which we kind of studied in tropical situation. I think mathematicians they kind of studied kind of a cases when the target space is not P1 but elliptic curve. So that is essentially like going to one-dimensional Calabi-Yau, or to go into one-dimensional Calabi-Yau, and in their cases their answer is kind of more complicated, and they have all these issues. But kind of we are dealing with a situation that everything is toric Fano, and that situation allows us to bypass all these issues with kind of virtuality, virtual classes, virtual cycles, stacks, and all these crazy things that could and will happen to a moduli space if you relax one of the conditions, genus zero, no descendant, toric Fano. So relaxing kind of one of them immediately gets you into a territory where things became way more complicated. I think we should for sure make a break. The lecture should have a break. Okay, so since we are making only one break, let's make it longer. Let's make have some questions at the end. Okay, let us. I need to write something. Although just want to finish. I think we discussed. Let me start the radio. Okay, so we kind of defined what the tropical curve is. So now the next step towards and discussing elementary problems is to talk about modeling of tropical curves. So we have this tropical curve is essentially like class equivalence class of some data assigned to a graph. And now we want to figure out how much freedom we have in assignment of this data and what kind of freedom we have. So the data that we assign that I'm currently raising is kind of mixture of discrete data and continuous data. So kind of declarations. So they essentially they are kind of go into discrete and kind of continuous. So for discrete decorations, we have like directions, and we have integer vectors. So for each edge, we assign integer vectors, and kind of roughly to a discrete data, we can add different types of graphs. Okay, so as I say, we will mostly focus on Geno 0, so different types of trees. So different types means that if we fix, say, a class of the curve, so we fix a number of leaves, so then there could be still different types of trees with the same number of leaves. And the prime example is basically a case when we have 6 leaves. So then we have 2 kind of different types of trees. A tree like this with 6 leaves, and another tree like this, and they are different trees. So that's why roughly into discrete data we will also kind of put this data about different and equivalent trees. And continuous data is essentially assignment of this length and width for each edge. Internal edges of gamma. And we have kind of this center of mass assignment or assignment for position or for image of some special vertex. And we denote it like this. And data belongs to Rn and dimensional torus, and this data belongs to R plus times S1. So that is our continuous data. So it's given by some continuous numbers like length and width and position on a torus or position on n-dimensional plane. And some discrete data like choosing direction, choosing integer vector, and kind of specifying type of graph. So not surprisingly that if we specify kind of curve class, so curve class of our tropical curve gamma to be beta, so that is essentially specifying number of leaves and kind of integer vector and b vectors assignment. So therefore we want to kind of study similarly to what we did in a complex case. So in a complex case we talked about kind of curves inside of some toric variety X with a given curve class, or like roughly speaking curves of a given degree beta. So with beta second homologies of X. And here we are talking about genus zero curve, so that's why I will just drop a label of a genus. And so far we haven't talked about any marked points. So let me even not introduce this label. So for now, our label is kind of X and curve class. So then this moduli space is the following thing. So first of all, it is toric variety. So when we assign it all these lengths and width, we kind of assign them in a way which is naturally splits into some kind of radial part or some variables that live on a radial line or in a positive radial numbers and some faces, whether it twist or position in n-dimensional torus. So it is toric variety, so it has like radial part and some kind of torus vibration. On top of this radial part. Okay, so that's why for radial part I will put upper script r, so x beta kind of radial part. So for radial part, we say the following thing. So we take a union over kind of discrete data, and here we kind of take a union of a gammas whose first class equals to beta. So different gammas means kind of different assignment of integer vectors, different assignments of directions, different choices of graphs. And then for a fixed discrete data gamma, so we have this continuous data. In a radial case, continuous data is just this part. So this m. Now it is x gamma. So it is tropical curve in x of discrete type gamma. And then this x gamma, it has very simple structure. At least before we compactify this moduli space, so its structure is very simple. So it is essentially kind of Cartesian product of n-dimensional Euclidean space, which is kind of space of locations of our center of mass. And then we need to assign kind of R plus. So to kind of simplify my life, to have less brackets on a board, I think standard notation for positive real numbers is kind of R plus with upper plus. But because I will often use like powers of R plus, I will sometimes introduce an alternative notation, which is R with a lower plus. And here it is number of internal edges of this graph gamma. And coordinates on this moduli space is naturally RC that lives here. And here we have like this TE, which are kind of lengths for each internal edge. Okay, so therefore here to get a full moduli space, we need to kind of glue these moduli spaces for different curve types, and then we need to add some kind of limited points. So we need to kind of compactify this union. So this will be essentially union of some open sets, and we need to compactify it into moduli space. Okay, so let me kind of give some examples. So the first interesting example is kind of degree 2 curve. So x is C2. So the type of the curve is defined by a single integer number. So let's say we have a degree 2 curve. So its curve class is twice times the standard hyperplane class in P2. So for that is degree 2 tropical curves. Okay, so so for degree 2 tropical curve, we have so graph gamma has 6 leaves, and with 2 leaves, of each type. So each type means it's choosing from 3 primitive normal vectors. So we have a graph. Okay, so this curve is always genus 0. So we have a tree with 6 leaves, and then these leaves are decorated by these 3 integer vectors, such that we have exactly 2 leaves of each type. So let us see. So as I said before, so to describe all curves, we need to start with kind of topological data. So we have 2 graphs with 6 leaves. So therefore, what we need to do, we need to kind of decorate using all different in different ways this sort of 2 graphs. So because we as I said before, we defined our tropical curves as an equivalence classes. So let us kind of simplify our life by choosing. So we have the special vertex, which we kind of prescribe it this radial and angular position. So if we have a special vertex on a tree, we can always choose directions kind of from leaves towards this vertex. So what we do, we kind of start with this vertex and make all edges incoming. So then here we will also make all other edges incoming. Yeah, okay, I'm not sure whether it's unique, but okay, okay, maybe it's not unique, so we still need to check different. Okay, but let's choose some decoration. So let's choose decoration to be kind of mostly incoming for this vertex C. And then what we need to do, we need to kind of check the following thing. So we need to assign these integer vectors, and then yeah, maybe I missed one of the consistency conditions. Now I can realize it. Okay, my bad. So additional consistency condition. So usually this consistency condition is kind of in quantum mechanical description will give 0 contribution, but for very tropical curves we need to give it that for all edges, for all internal edges, or for all edges. So we are not allowed to have 0 vector assigned to an edge. So this condition would kind of rule out some assignments. For example, I can assign something like this. Let me give this vectors a names. Let me call it v1, v2. Now I don't remember whether I call it v0 or v3. So give me a moment. Just to be consistent with later discussion. Yeah, I think I still call it b3. So b1, b2, b3. And kind of, you see these three vectors, they have the following property that b1 plus b2 plus b3 is 0. So therefore here, we can try to assign the following vectors. So we can assign b1 incoming, b2 incoming. So then here we will have b1 plus b2 outgoing. And then here we can assign b3. And then here on this edge, we will have vector b1 plus b2 plus b3, which is 0. And that is kind of not a tropical curve. So therefore this consistency condition is important. However, kind of if we assign, say, b1, b2, so that is a very tropical curve, and the vector here would be 2b1 plus b2, and this thing is kind of not a 0. And here you can kind of continue. Yeah, so here you can probably continue with any assignment we want. So we have 2b1, so then we can assign b2. No, sorry, too many b1. b3. So then here, when we will add b3, we will have b1, and then b1 plus b2 plus b3 will add up to 0. So that will be very tropical curve. So we start with a graph, with a tree in this case for genus 0, and then we assign integer vectors. Then first assign orientation. So because of equivalence, we can kind of freely choose orientation. So we choose some orientations, and then we start assigning vectors, and just putting this vector balancing condition would give us kind of unique solution for vectors assigned on internal edges. So kind of we choose the G with a fixed number of bits, given number of bits. So then kind of assign directions. So there are no constraints, so we can assign directions any way we want. And then assign primitive normals to it. And for kind of use balance conditions to solve for vectors on internal edge. So if we assign the directions, we assign the sums, we assign the signs in vertex balancing condition, and then starting from leaves, we can kind of traverse traverse this tree and recover all internal edges. So in the case of a tree, is kind of procedure rather straightforward. However, there is this small subtlety that in some situations, when you add up this kind of integer vectors assigned to edges, you may run into situations that you kind of assign it vectors to edges that add up to 0, and you run into edge with 0 assignment. So that is not a valid term. So here, kind of generally, you assign plus minus. Okay. So I could have chosen orientation in this way. So okay, so that will give us a kind of these different discrete types of our tropical curve. I'm not sure, okay, because the answer is kind of written on paper, so it's not kind of proper homework exercise, but an example. So in the case of so in this example, we kind of continue here. So the number of discrete types. So we have exactly 4 discrete types. So we already saw 2 of them, but let me for the sake of saving time, just copy picture from my notes. So 4 discrete types. So we already saw these 2 discrete types. This. Okay, so we did one type. So then we have picture like this. So the second type, so these 2 pictures we got by kind of resolving kind of singular tropical curve like this, resolving it in 2 different ways. So and that would be precisely a point which we would add when we will compactify union of this space. So here this internal edge will have some length TE, and here will be like T prime, so it's edge on a different tree. And then if you take the length of this edge to 0, so both picture, so that is T E prime going to 0, and that is T E going to 0. So when we take these edges to 0, so then we will reproduce a kind of singular tropical curve with covalent vertex. And that's kind of where these 2 different components of a model space would glue together into single connected component. So let me draw this edge in a different color. So now we can do the following thing. Like here, you see, we only kind of taken the limit of one of the 3 edges, like taken the limit when length of one of the 3 edges go to 0. But we have like more internal edges. So each of the trees has 3 internal edges. So we can imagine a situation. What would happen if we take a length of some different edges to 0? So let us investigate this situation with yellow edge going to 0 lengths. Okay, let me call it T1, T2, T1 prime, T1 prime. So let us kind of investigate situation when T2 goes to 0. So when T2 goes to 0, we will have a picture like this. So we still have this piece of the curve that doesn't change, we have T1. And now T2 goes to 0. So we have kind of these two vertical edges. They kind of next to each other and they are parallel. So that is also a singular tropical curve because we have a 4-valent vertex for red 4-valent vertex. However, we can once again resolve a 4-valent vertex, and in this situation, this deformed 4-valent vertex, so this yellow edge gives us one type of a deformation, but there is another type of a deformation. So therefore, let me draw it like this. There is another type of deformation when T1 prime goes to 0, and it is deformation from the following interesting curves. So let me draw this part into more details. Yeah, let me draw it like this. So here, what I have like two edges with let's put orientation like this, with integer vectors 0, 1, 0, 1. So then they meet at a vertex which is 3-valent vertex and produce a new edge with the integer value vector 0, 0, 2. And T2 prime, so this red edge, we call it yellow, is the length of this yellow edge. So if we take the length of this yellow edge to 0, we get this situation. So therefore, these two components, they also once again join together over this singular tropical curve that acts as t goes to 0 compactification of moduli space. So I think at least in the two case, like this full moduli space, the kind of compactification is kind of TE goes to 0, like compactification by edges of 0 lengths. So here we kind of look at codimension 1 boundary, so we take one edge to 0 lengths, and we can kind of take two distinct tropical curves and take edges to 0. So you can kind of play with this game. So you can kind of take a length of one edge to 0, and then get 4-valent vertex, which you can deform in a different way. And if you perform all these operations, eventually you will get, it will be like 7 types. So here I drawn 3 types. So it's like 1, 2, and 3. So that is the situation when you have finite lengths. And just to kind of give you picture, let me. Yeah, I think another situation would be if I take this edge, so I can shrink the blue edge T3 to 0, get a singular curve. And then I can resolve it in different way. So deform it in different way, and the picture will be like this. Here 45 degrees, here faster, and I think, yeah, now we have 2, 2, 2, 2. Yeah, so that would be different resolution, and now this will be my blue edge. So if I shrink this blue edge, I will get this picture, which is the same as shrinking this blue edge. So I want to say that T3 prime goes to 0, will give me this picture. And therefore you can proceed in two ways. So one way you can just start with these two types of graphs with 6 leaves, and then kind of start assigning integer vectors and kind of see what you can get modular equivalence. Or alternatively, you can start with one of the curve and then kind of go take one of the edges to 0 lengths, go to a singular curve, deform it in a different way, and that would be another way to kind of traverse the full moduli space. So in this case, there will be totally kind of seven types. So in this union, there will be union of 7 types, and these 7 types they are kind of grouped in a complicated way by different kinds of singular tropical curves. So kind of luckily for us, even though we have this very complicated structure for joining these different parts of a moduli space together, the forms that we are going to integrate, so they will be kind of good enough that the answer of the integral would be insensitive to this higher codimension structure. So therefore, in performing integration, we can essentially integrate over this open strata and just add up different discrete types. So that is kind of good part that at least in the case of, once again, toric, Fano, G 0, no descendant invariance, so we can kind of perform these integrals for each discrete type independently and then just sum up.
So yes, later like philosophy, the UV boundary will always not contribute to some modular space integral. Because IR part, it seems now it there does not exist such IR boundary.
Yeah, so in this case there is no kind of IR boundary. So it's only UV boundary. Okay, so here maybe I kind of cheated slightly. Okay, let me correct myself and make statement more precisely. So okay, so let's make it more precise. So when we will see actual enumerative problem, which probably will happen next time, given that we have 8 minutes. So we will see that, so in kind of complex geometry setting, when we ask how many degree 1 curve passes through 2 points, the answer is always 1, as long as these points do not coincide. So there is only special case when points coincide, then the answer is ill-defined. So in a tropical setting, the kind of the enumerative problem that we're going to solve is the following. So I kind of put 2 points inside of this triangle. I ask the question whether there is like a star with the prescribed directions such that it passes through these 2 points. So in this case, for example, to get such star, okay, I can get such star, maybe something like this. Yeah, so that would be star through these 2 prescribed points. So there will be a special situations. So obviously, like a special situation when 2 points coincide, that gives us kind of infinitely many stars that pass through this point. So that is kind of infinity that we see in complex geometry. However, we will see additional special situations, and these additional special situations would be when these 2 points are on a line with a tangent vector equal to one of the compactifying tangent vector. So in this situation, kind of you also formally get an infinite answer. Kind of you can draw this vertical ray of a star, kind of passing through these 2 points, and then you have a freedom of kind of moving this picture upward. So that gives us one-dimensional freedom. So in this sense, in a tropical case, there will be additional exceptions. Additional to obvious exception when 2 points coincide. And additional there in a sense that 2 points, like 2 points always lie on a line, but they lie on a line with some specific slope. Like they lie on the line with a slope, with kind of vertical, horizontal 45-degree line. And that would be precisely a situation when the integral kind of to reproduce the answer from complex geometry. So here we will run into problems that the integral kind of over full moduli space is actually getting its major contribution from kind of singular curve, from this compactifier. And that kind of known issue in tropical geometry. Then when people kind of say set enumerative problem in tropical geometry, they kind of still mention points in the general position, but for them general position means not only points don't coincide, but points don't lie on a line with a prescribed tangent vector. However, if you want to get like the same generality, we can do the following thing. So instead of looking in the Gromov-Witten theory, the invariant was defined on cosmology classes. So we can kind of use observables which upon correct dual to a points, which will be singular differential forms with a support on a point. So that will strictly speaking match with enumerative problem of passing through some point. But we can kind of deform this differential form, which is delta function upon correct dual to a point, to a kind of smoother form that has like bigger support. So we can kind of smear the support of this delta function, delta form at the point, to kind of delta form in some kind of neighborhood of a point. So that we can do while keeping the form in the same kind of cosmology class. So the kind of the answer in the Gromov-Witten theory will be insensitive to such deformation. So regardless whether we use singular form or we use smeared form, we will get the same answer. However, in the tropical geometry, like if we smear our observable a little bit, so then we can completely avoid this situation. That the smearing would make a kind of contributions, would make like a proper contributions in this kind of open components of a moduli space, and the answer wouldn't suffer from these issues. So that is something that people haven't done, and that is something that we kind of at some point plan to do, but we never actually managed to kind of carefully write it. So it kind of still left the remark in our paper that seems to be a plausible solution to that issue, but we were distracted by some activity. So that was the reason why we essentially ignored like all this compactification business, because in a case we kind of run into some non-generic situation, we can always kind of smear the forms and kind of avoid this situation. Okay, so we have this moduli space, and just to finish this example, so here we will have 7 types in our example, and each of the moduli space will be very simple. So in this case, so radial part of a moduli space for any gamma inside P2. So that would be R square times R plus cube. And that kind of for all gamma. So, and indeed we see that if we perform this procedure of taking the limit of one edge goes to 0 length, and then we deform it again to a finite length, so the number of internal edges does not change. So, or equivalently, you can say that the number of internal edges is uniquely determined by number of leaves, which is kind of uniquely determined by curve class. And that kind of behavior that we expect from moduli space, that we have kind of, if we fix the curve class, then we would have like a moduli space of fixed dimension. We may have like different strata depending on kind of the shape of the curve, but the number of moduli should be the same. So in this this kind of, okay, let me call it proposition. So that's a statement, and you can kind of prove it in the following way. So I'm not going to complete the proof, because I think it is part of the homework exercise in some different setting. But just kind of idea of the proof is that we have two relations. So first we have a relation. We have this by definition all vertices are trivalent vertices. So it means that for each vertex there will be 3 edges connecting to this vertex. So then every internal edge would connect to at least 2 vertices. So that's why this kind of half edges that connect to each vertex. So the total number of such half edges will be 3 times number of vertices for gamma. And then each internal edge would contribute exactly 2 half edges. So it is kind of connected to 2 internal edges. While okay, internal edge of gamma, V of gamma, and we will also have these which I often call external edges. So each leaf will contribute to a single half edge because it just connects to internal vertex by one of its ends. So that will give us a kind of a one linear relation between number of vertices, number of internal edges, and the number of external edges. So what we want to see, we want to determine number of internal edges in terms of number of leaves. So the good thing is that we have one linear relation, but unfortunately we have 3 variables and 1 relation. So second relation is essentially using the fact that we are looking at a tree. So genus is 0. So in the simplest case, number of loops is 0. And I think last time or time before last time we kind of derived the formula for a number of loops in terms of edges and vertices. So for a general graph, so what is the number of loops? So it kind of grows with the total number of edges, because we can have 2 vertices and just add more and more edges by creating more and more loops. So that's why it is kind of linearly grows with number of edges. It decreases with number of vertices, because I can simultaneously create like vertex and edge by putting a point on some edge. And here somewhere should be plus or minus 1. Let me recall. So if I have a situation with 2 vertices and 1 edge, that will give me no loops, so therefore I should put +1 here. So now here it is a total number of edges, a total number of vertices, and in this formula we should kind of formally assign kind of one valent vertices at the end of the leaves to make this computation. So, or equivalently, you would say that the leaf, they will contribute to one valent vertices and will contribute to semi-infinite edges. So therefore here I can completely eliminate the leaves and put it like number of internal edges of gamma minus number of 3 valent vertices. 3 valent vertices of gamma and still keep +1. So that gives me another linear relation for the same data. So it gives me linear relation between internal edges and V3, and having two linear relations in principle allows me to solve for number of internal edges.
Yeah, the second question, I think there's no such +1 shift because in the example you can see 9 vertices and 9 edges. So there.
Let me see. No, there is a +1 shift. Like if you have a star, so star has one 3-valent vertex and no internal edges, and star is a tree, so it has 0 loops,
Yeah.
1 V3, and no internal edges.
But why here it seems we
We have what? We have 3. Okay, let's look at kind of
general.
general graph. We have 1, 2, 3, 4.
It's still not a general.
No, this one is sufficient. Is a general, so all vertices are 3-valent. So we have 1.
Maybe you can use the upper one.
Okay, we can use the up one. So let me erase that one. So here, what is the number of V3 of gamma? So we have 1, 2, 3, 4. So number of internal edges of gamma is 3, and the number of roots of gamma is 0. So indeed we need +1. Yeah, but kind of the idea is that you kind of get typically two types of linear relations. So one linear relation that is kind of Euler type of the formula that relates loops with total number of edges and total number of vertices, and another condition is kind of a balancing condition for half edges. That vertex. The 3-valent vertex basically tells you that 3 half edges meet at a vertex, and an internal edge means that it is kind of union of 2 half edges. So that kind of typically a way to get kind of linear relations between internal edges, external edges, and vertices, and typically you want to eliminate vertices because external edges, they essentially are determined by curve class. And in all our formulas for a moduli space that we had on earlier lectures, we kind of have a contribution from a curve class which was something like beta integral of C1 of x. So a typical formula for dimension of moduli space, like if we fix genus, was essentially this thing plus some fixed constant. And this thing is essentially kind of number of external edges. So in P2, like C1 was 3 times hyperplane class, and beta was kind of C1. C1 of x was 3 times delta function hyperplane class, and beta was degree times hyperplane class. So this integral is like 3D, and that is precisely a kind of number of external edges for tropical curve of degree d in P2. So I think next time we will kind of finish. I will write like careful. Oh, maybe I can write it for P2. So for P2 you can perform this computation, and what you will get. So homework exercise is anyway for doing the same thing for P1 cross P1. So if information carefully. So then, so once again, as we say, the full moduli space is a toric variety. So it is some torus vibration over this radial path. So therefore, we can say the complex dimension of this tropical moduli space is essentially real dimension of its radial part. And we saw that, that kind of different discrete types, they have the same real dimension. So therefore, we can just compute real dimension of discrete type gamma, some discrete type gamma, and then because of these relations, we would see that this thing scales with the number of external edges. So that will be like number of external edges of gamma. And now I need to see what this thing. I think it is number of external edges of gamma. I'm confused by this one. No, I think that's correct. By minus 1, and this number of external edges is precisely 3 times degree, so it's 3d minus 1. And that's kind of what we expected in P2 case. So that is kind of genus 0. Because we are kind of here assuming that all our graphs are trees. And that is familiar 3d minus 1, which is number of points that we need to specify to uniquely fix the curve. So you can say that the question about given curve passing through 3d minus 1 points is like using this 3d minus 1 points to fix 3d minus 1 moduli of the curve.
Excuse me. What does mean of complex dimension of that?
Yeah, so let's say like this tropical moduli space is a toric variety. So it means that it is torus vibration over some radial base.
You mean it's a variety?
Yes. So therefore its complex dimension will be the same as this kind of real dimension of a real part. And for real part, we kind of computed the dimension by counting number of moduli as kind of number of internal edges plus n additional moduli, which is overall position. So in kind of our example, so in simplest example, which is degree 1 curve, so we actually don't have any internal edges, so we only have a kind of radial position for this point and kind of dimension of a moduli space. Dimension of a moduli space, complex dimension is just 2, and that precisely corresponds to a free choice of this radial position for this trivalent vertex. And this number also matches the kind of total number of external edges, which is 3 external edges minus 1. So that is external edges minus 1, and that is matched like 3 times 1 minus 1 for this photo. So more interesting it became in this case for degree 2. So complex dimension of degree 2 is 5. And this 5 kind of works in the following way. So we have kind of overall position or position of some vertex, which will give us two radial positions and two angular positions. But we're looking at the complex dimension, so we just count radial position, and we have 3 internal edges. So that will give us 3 moduli for internal edges length, and there will be twist kind of fiber to the length in a sense of variety. And similarly, this number counting like number of internal edges and kind of components of position of one special point So we can also express it in terms of number of external edges. So here we have exactly 6 external edges minus 1. That also gives us 5. Yeah. So in your homework you will be asked to kind of perform this exercise, and kind of the last problem would be perform it in slightly bigger generality for not restricting to genus 0, but doing this arbitrary genus curve in P1 cross P1. So it's a bit of generalization from P2 case. So in that situation, instead of the curve class is determined by a pair of natural numbers, which is by degree, which is essentially a kind of number of vertical and horizontal lines that go to infinity. Okay, and your homework was okay. The homework is okay because it was posted on Saturday or Sunday. Okay, well, I think on. No, sorry, it was posted on. Yeah, I think it was posted on Tuesday. Next Tuesday. So okay, so you still have like 3 days to solve it. So it is essentially like redoing this analysis for P1 cross P1 case, maybe in simplified way, because I haven't asked about full moduli space. I only asked you to compute the kind of to compute the number of internal edges as a function of degree. So. But number of internal edges is kind of simply related to dimension of a moduli space, because it is different by sort of overall shift, which is kind of number which is just a position of special vertex or dimension of target space. Okay, I think I'm already like way over time, so I should stop. And
I want to know what's the relation between this and the moduli space and of stable map.
I think okay, at least in once again in the cases which I am familiar, which is Fano, toric varieties, I think you can do the following thing. So you can start with a moduli space of moduli space of complex curves, and then you can tropicalize this space, and then tropicalization of this space would kind of match with this tropical moduli space. So the kind of the simplest example of this phenomena, I think is the following thing. So we can look at kind of let's take even our target space to be a point. So let us look at a moduli space of 4 points on a sphere. So this moduli space, if we kind of compactify it, that will be once again a sphere itself, and non-compactified would be a sphere with 3 points removed. So we know kind of how tropicalize P1. So tropicalization of P1 gives us some kind of star, and so that is tropicalization. And this star has a very natural interpretation in terms of this moduli space. So in this moduli space, we have kind of bulk point. So when there is no kind of special value for this cross ratio. So when 4 points are in general position, and we have points that are close to boundary. So we have a situation where this sphere is kind of became something like this. Yeah. So that are kind of points close to the boundary. So that is the situation when kind of like 2 points like nearly collide. So it means that there is kind of a and in this situation we can choose exactly 3 pairs, because here it doesn't matter like which point we call 1, which point we call 2. So there are exactly 3 ways of splitting these 4 points into pairs. And these 3 situations will be precisely kind of, so here will be this special value of cross ratio, and this special value of cross ratio will be precisely coordinate on these 3 rays of P1. And that this kind of simplest example how the kind of tropicalization of P1 kind of reproduces points that are close to the boundary of a moduli space. So essentially, after tropicalization, all these smooth points where 4 points are in a general position. Under tropicalization, they all map to this single vertex. However, these interesting cases, interesting in complex geometry cases when points collide. So they precisely go to something interesting in tropicalization. So in a sense, tropicalization kind of maps boring parts of a moduli space, like boring parts means in the parts where curve is smooth, maps it to something trivial in tropical case, to like a single vertex. And interesting parts where moduli space is almost degenerate, it maps to some interesting kind of parts of our tropical curve. And the same story kind of holds for higher dimensional moduli spaces. So that was also studied by Mikhalkin, that at least for moduli space of kind of complex structures, so there is always nice tropicalization, and all these different cross ratios, they naturally became something like coordinates on this infinite rays. And different types of rays kind of describe different discrete types of degenerations. And I think people explicitly constructed like M0n in this tropical prescription. So that is essentially some polyhedra that you get, because for 5 points you should get something with complex dimension 2. So therefore, on a tropical case, it's not tropical curves, it will be tropical circles. And for higher and higher dimensional moduli space, that will be like a tropical variety of higher dimension, which is kind of not a subject of our study. But people kind of discovered some interesting properties in kind of tropicalizing moduli spaces, and kind of and even given some interpretation.
We need to fix the number of marking.
Yeah. So you need to fix
But
number.
in the tropical setting, the number of marking is like intrinsic information.
So there is also some interesting part which is kind of related to another work of Andrei Lossev, which is related to the holomorphisms which Louis is working on. So there is this kind of interesting story that that in a tropical case, or maybe to some extent even in complex case, sometimes you can relate the following objects. So you can relate a moduli space, let's say here, just projective variety for simplicity. So MP2D with n marked points. So there is a kind of some isomorphism of this space with the space M n plus 3D. So here we are talking about kind of moduli space of maps. Okay, so in this case, like okay, all maps are stable. So moduli space of maps to P2 in degree D. But there is a way to reinterpret this moduli space as a moduli space of just complex curve with a bigger number of marked points. So kind of the data about target variety and degree kind of combine it nicely into number of marked points. so that is at least this property was kind of. I'm not sure where it was first discovered, but I first saw it in works in the tropical geometry. So at least people kind of carefully proven this in a tropical setting. But I think to some extent, at least at a level of integrating some kind of sufficiently smooth forms of the moduli space, we can do this replacement. I think in the moduli space for complex varieties. So that is kind of the strange correspondence that allow us to kind of treat this whole graph as some kind of complex curve with like 6 marked points. Which is kind of not surprising because like when we talked about structure of a tropical curves like few lectures ago, so we talked that there is a kind of circle vibration on top of it, and this thing is essentially some kind of sphere, like Pen's decomposition for a sphere with some cups. And because these cups, they are very far away at infinity, so this thing looks like a sphere with 6 punctured points, and these punctured points is where the 6 cups are. And surprisingly, like moduli space of this sphere with 6 marked points precisely matches the moduli space of kind of degree 2 tropical curves in P2. And this idea was essentially used by Andrei Lossev and Edward Frenkel in their proof of mirror symmetry. So they kind of turned integral over this moduli space into more familiar integral over moduli space of complex structures, and then kind of performed some manipulations with the integral here to get another integral that gives us Landau-Ginzburg Saito type answers. So in a tropical case, like in our approach, we are not going to use this relation. So we will mostly deal with these integrals by themselves without explicitly mentioned. But you will see next time the structure of these integrals will be like almost the same as the structure of these integrals over n plus 3D dimensional moduli space. So that is something used by Lossev and Frenkel in mirror symmetry proof. So that is something that people use, people who doing like mathematicians who doing tropical geometry. So they often use this as a part of their kind of constructions and various proofs. That kind of an interesting remark about relating two different types of moduli spaces, but we are not going to use it in our course. So that's why it still stays as a remark. But that is this extended answer to your question whether there is something interesting, some relation between tropical moduli spaces and complex moduli spaces. So often kind of tropicalizing moduli spaces gives you something interesting and something useful.
That confused it from 3D minus 1 is not the dimension of the stable map. It's like a solution of the equation.
No, 3D minus 1 is a number of stable maps without marked points.
But I mean, how to get 3D minus 1 in...
Yeah. So here I cheated a little bit because to properly get 3D minus 1, so 3D minus 1, you need to first introduce marked points to put observables. So that's why it is 3D minus 1 plus n, where n is a number of marked points. So that is complex dimension of moduli space of stable maps with n marked points. And then each marked point you insert like degree 4 differential form, because it is delta function on a point in two-dimensional complex space. So therefore, the kind of proper way of getting number of points in D-1 is first to take this thing multiplied by 2, that is real dimension of a moduli space with n marked points of maps P2 to D of G with 0. And then here you have like n observables, and each observable contributes is a degree 4 differential form. So therefore here, yes, you will get like n equals to 3D minus 1, but not through just relation number of observables equal to dimension of moduli space without mark. It just happens that in 2 dimensions some things are secretly cancelled. But I agree that this argument wouldn't generalize to higher dimensions, because for higher dimensions this number will still be 2, because each marked point will contribute to real dimension by exactly 2n. But here dimension would depend on dimension of a target space. So if it point in P3, then it will be 6n. And then
it's a co-dimension.
Yeah. So I agree that there was like slight cheating or simplification. There we go. But yes, you're right. To kind of get the number of points, we first need to introduce moduli space with marked points, and we will do it, but not today. So that is our plan for next time. So we will introduce marked points. We will introduce tropical observables, and then we will perform integral of a moduli space, and we will see, like explicitly, we will see how these issues arise if we integrate singular tropical forms of a moduli space, and kind of we will talk about how to avoid these issues also.
So in your graphical tropical in this picture interpretation, what we care is the green point. It's not the bulk.
That depends on what you are doing. Like if you are integrating a smooth form of a moduli space, yes, then you generally care about kind of open component. But in some situations, you kind of integrate a form that has support only on a singular part of a moduli space. And that, I think, what typically happens in these cosmological field theories, because one of the axioms is that your form should properly degenerate as you approach boundary of your moduli space, and that usually after multiple degenerations you get kind of a form on some regular moduli space, which at the end of the day means that your integrand should have an interesting support on a boundary of a moduli space. And that's why for cosmological field theories, you are interested in integrating something over boundary components. And in that situation, kind of going tropical is helpful, because in that situation you kind of suppress the part where your integral doesn't contribute like bulk part, and you kind of zoom out or zoom into the boundary components. So previously boundary components were something complicated and singular, but in a tropical case, like boundary components became something nice and smooth with some nice coordinates, and that allows you to explicitly perform the integral over these components in a tropical setting.
Yeah, so later typically we will integrate over some singular the divisors inside the total modular space.
Yes, and that's why it will become like integrating over some nice tropical curves or nice tropical variety. Okay. But unfortunately we are not going to use it in our course. So that was what kind of logic used in their construction for A and B mirror. But in kind of tropicalization of that construction, so we don't need that relation. So it turns out that tropicalization makes the integrals of a moduli space of maps kind of tractable by themselves, and we will just work with the moduli space of math.
So in some sense, the calculation of total dimension is useless because later we will use singular strata.
No, singular strata is used in cosmological field theories, in complex geometry. But in the tropical geometry, we will use smooth forms and smooth strata. So it is in a complex geometry, we want to integrate over this boundary strata to get something interesting. But in the tropical geometry, something interesting already happens in general strata without going to a boundary.
Yeah, because like WDVB, those algorithm vector invariants, the settings are like complex geometry. So, but now in case we are doing integration over bulk.
Yeah, but WDV is a quadratic relation on invariants. So you go to a boundary strata, which is by axioms homological field theory, is kind of a product of two kind of smooth integrals over smaller dimensional things. And here we are not talking about quadratic relations. We are talking about this smooth parts which are Gromov-Witten invariant themselves. So in this course, we are not going to prove WDVB or other than doing it in Landau-Ginzburg side of theory. So we are not going to do it in a tropical setting. So that's why we never need to go to any singular strata. So we will like perform an integral over this smooth open part of a moduli space, and that will give us kind of the answer that we want, modulo this small issue that we either should ensure that points are in sufficiently general position, or kind of spread out a bit our observables to make them kind of to make a support not a single point, but let's say some small neighborhood point. So that would also equivalently remove this subtle situations.
Yes, like integration of the bulk is like a counting of tropical curves, but so we don't expect that it will recover something like in complex geometry.
No, it will exactly equal to so we will see next time when we perform the integral, we will see one of the example of this what people call tropical correspondence, that tropicalizing curves, tropicalizing moduli space, tropicalizing observables, and performing integral in a tropical setting, Kontsevich-Manin integral in tropical setting, exactly equals to performing the integral for the same setting in complex geometry setting.
I see. So it's very non-trivial. Like the bulk integration.
That is not trivial because generally, like this example generally shows that under tropicalization, like different regions kind of tropicalize differently, and the fact that even after tropicalization you get the same answer is some kind of surprising fact, because like there will be a certain non-trivial transformation for observables. So
I see. So it's like a translation from the singular strata to the like a bulk smooth integration. You previously they are like in the singular strata. The invariant are like hidden in the singular strata, but you perform something like a smooth integration, then it will recover such quantity. You construct another moduli space which we call tropical moduli space, and you perform bulk.
Yeah, but in Gromov-Witten theory, you can also choose different representatives, and instead of kind of singular forms, you can choose some kind of spread forms that represent the same cosmology classes. So that's why, in principle, in ordinary Gromov-Witten theory, you can also avoid all these issues by also spreading your forms, and then all integrals would get a contribution from just kind of open sets which are probably of generic curve without any special degeneration. So that's why that part is kind of not very specific to tropical case. Okay, but we will see more next time when we will get like explicit examples of moduli space, where we'll get explicit examples of enumerative problems and kind of observables and moduli space integrals for this observable. So we will compute some integrals in a tropical setting, and maybe we can compare it with this kind of integral in a complex setting. Okay, so
I say why this example we don't consider both T1 and T2 become zero, and there will be a 5 valent word.
yeah. So that will be like higher codimension strata. So far we only looked at kind of codimension 1 limited point. But yes, I agree that okay, I erased like this curve. We can feel that degenerated if we take like this edge to 0, and at the end of the day, there will be like up to codimension 3 strata when all 3 edges go to 0, and the curve will be like star with 6 rays. So that's kind of where all components would eventually meet. So and then you can start with a star of 6 rays, and then you can start deform it. And by deforming it, you can recover like all types of the curve. So the whole moduli space will be like have this complicated stratified structure where different components meet over different codimension boundaries. So with usually some kind of manifold with corners and the different kind of faces of this manifold with corners would give us different number of edges whose length go to 0. Yes, but you are correct that here we only talked about kind of codimension 1 boundary, but there are like higher codimension 1 boundaries as usually for manifold with corners.
It's like we compactify this moduli by a stratification. We add some lower dimension boundary.
Yes, we compactify it to manifold with constants, like as usually, like here, natural coordinates are kind of R plus, which is like coordinates of half space, and then we add like boundary of half space, and we will get another half space to whom we can add another boundary. So that gives some kind of corner structure depending on how many variables you set to 0. So.
In this case, it's just the R plus 3 and the 5 valent vertex has only one case. A single type, and there should be 8 types in together.
8 types. Okay. You're saying that if I start with 6 valent vertex, then. But I think probably 2 of them would be equivalent. So when you doing the deformation multiple types, there is kind of no guarantee that you wouldn't get equivalent curves. So I think among kind of 8 types that you expect, there will be like 2 which will be equivalent. Okay. Okay, thank you.
话说这个课现在有啊，这课现在有录屏。
对，这个乱词是。
哦，OK，我们之后的也都有录屏，我可能线下就不太会啊。
这是独属于哲院的松弛。我看一下空调。好的。但有一件非常怎么说呢？我们对于哲院来说有一种非常松弛的样子，就是我们反正所有的学分几乎所有的学分要求都是跨专业。为了满足哲院最低的哲学要求，我们又自己开了好几节课。但是问题是我们就这么点老师，所以老师不一定上得过来。
那就学生减少嘛。
那也不是，就是很少有这么干的。但是我想快点把课上完就拉倒。不然太累了，就是一直有门课吊在那儿，就很难受。就早上晚早哪在？早上晚我就可以一直待在这儿，或者一直待在那儿。反正我能进这个楼，到时候还给桌子以后，我就一直待在这儿。哦，对，好像并没有人跟我这么说。然后陆地是阿姨擦桌子的时候，被移了一下，应该是。
不过感觉我们工位平常也没有人啊，大概像这一
差不多的是。理论上我可以掏随意一个人的工位，但是
他可能比较
对，所以我觉得 Honey 的比较没有心理负担一点。反正除了不能用打印机，我也不太是这儿的。都无所谓，哲人有免费。要拿回去哲人就行了。我租的那个公寓的钱还是能拿。
来，这样打印可以吗？我自己想打印还不见得打过来。大家都在被烫到的话，
上次带的那个基本就一个人，那一批基本上3、4个人顶天了。
我有点呆，感觉
你就放弃。右手少的速度，
基本上没怎么样。
就是那个动物汽车里单数的那2个，他们一直在，或者说他们在的频率很高。
我倒没怎么注意。
现在还不知道他们叫什么。另一个就是那个，好了，你这帽子好时尚。
这样用。
那我在想，我是不是需要搞一个大眼礼帽，然后去外滩逛一圈。
大家礼貌肯定有人要
啊，
肯定是
不跟体验的，这应该是冬天那种。长的风衣，然后里面带皮裙罩。要民国的话，腰间得别把枪。是。
说带礼貌就。
我记得他也姓李，好像。你说了我不有印象，我知道这些啊。好像是。对。就是对，李安说是才几个人，没有，就是做 pre 的有，做 pre 的不就一共4个吗？对啊，那个人就是有人，那个人我估计他只是坐在这儿，我都觉得他连不盘身都不知道，来听你开说这个东西。
不敢，肯定得。
毕竟把黑板上的东西抄下来，可能就要弄。我是反的，我不抄我没有办法记住。
这个我就不一样，抄不抄都会。
我现在发现读论文的时候，我抄论文我也没有办法记住，但不是来给自己记的，我再退一点。把一篇论文抄写一遍之后有点困难。
Yeah. Committed algebra. Yes, most probably, but at this time I cannot be sure. But yeah, I see. Yeah, definitely. Yeah. So I taught that last semester. Okay, so let's. Okay, so just to recall the definition of complex. Thompson. So omega is a defined to be so just to recall the definition. So okay, so pairs alpha beta where alpha and beta are both infinite tuples. Okay, so numbers. Okay, real numbers. So okay, so alpha and beta infinite tuples of real numbers, non-negative. Okay, such that the sum of these all the coordinates are bounded by 1. Okay, so each of the coordinates is bounded. Okay, so right, because each such a alpha I and beta I is bounded by 1, so therefore, as a subset, omega right is in the well, each of alpha and beta can be regarded as an element of right. So count many product of count many copies of the input 0, 1. And equipped with the product topology, okay, then it's not hard to check that omega is closed in here. So therefore, in particular, omega is compact. Okay, so in fact, omega is the compact. Omega is a compact effector metric space. Right, okay. Now, so last time I have stated the Thomas formula for the extreme characters of the infinite symmetric. Okay, so I gave a complete classification of the extreme characters of the infinite symmetric. Okay, so and of course we still have to prove it, and we're going to follow the proof of version and character, which actually give a more general versions of Thomas theorem. Okay, but in any case, motivated by the Thomas formula, so we first define again further following Bershing and Carroll. Okay, so following. sheet. So we first define a algebra. Okay, so the definition, as you're going to see, is certainly motivated by Thomas Form. Okay, anyway, so this algebra homomorphism is from our familiar algebra of symmetric functions. Okay, remember this is originally defined, right? So when we study the symmetric functions, right? Okay, so this sim to the algebra of continuous functions on omega on the Thomas index. So here this is the just space. So for us, we can take this to be the space of real value continuous functions on omega. Okay. Oh, by the way, this is just a remark. Okay, so previously you probably noticed that we did a lot of algebra. Okay, when we discussed sim and also the representation of finite symmetric group. But now we're going to do more analysis. Okay, not that much. Okay, but just say either functional analysis or some probability theory. So this is a kind of you're going to see. I mean, this the flavor of this subject is very much interdisciplinary. Okay, so we certainly need some algebra and combinatorics when we study this symmetric function. But now when we're going to employ tools from say probability or functional analysis. Okay, so therefore, say right. So these things will be you have to think more in a kind of analytical perspective. Okay, you want to appreciate these subjects. Okay. All right. Okay. So anyway, of course, this is with the usual norm, with the super norm. All right. So this is the final algebra. Okay. Just with the algebra operation, just the usual pointwise addition and pointwise multiplication. Okay. With the usual operation. Usual pointwise addition and pointwise multiplication of functions. Okay. Anyway, so we want to define an algebra homomorphism. Okay. So from sim to here. So that is the content of this proposition. So there exists a unique algebra homomorphism. Okay. So from this to this algebra of continuous function omega, then we're going to denote this one. So if f is an element sim, then the image in here we denote as f with a superscript 0. Preserving the scalars. Okay, so for us the scalars means just elements of R. Such that the following condition. So remember, right? We have this Newton power sum piece of k for k a positive integer. Okay, so piece of k is an element sim, right? It is homogeneous of degree k. Okay, just piece of k, right? If the original definition, right, is just the Newton power sum. So just these variables, take the sum of these, each of these variable to k up. Okay. Just okay. So the rule is that piece of k get sent to the following. Okay, it's the image of piece obtained here. So therefore, it's a function on right on the Thomas simplex. Okay, so this is equal to right sum alpha I to the k plus minus 1 to the k minus 1 sum beta I to the k. So here, of course, so if k is at least 2, okay, so here, of course, alpha I and beta I are the coordinates of omega. Okay? And if k is 1, then the image of P1, okay, is just identically 1. All right, okay. So there's indeed a kind of tricky thing, okay, but it's something that when I stated Thomas formula last time, so you remember that there's indeed, okay, so this type of expression occurring, and also, right, so this index, okay, runs from k, okay, at least 2, starting from 2, okay. Okay, anyway, so this first part of the proposition. Second part is that the image of this C omega things in the pseudo topology. So, okay, so the kernel of this Bravo chromosome okay, what is the principal ideal generated by the element E1 minus okay. Okay. The one here of course just means the scale. Okay, the scale. Okay, yeah. So as I say, okay, this definition of the algebra homomorphism is motivated by the Thomas formula. Okay, let me again just quickly recall. I will probably prove it later, but anyway, so recall Thomas formula. For the extreme carrier. Omega, the group, that's infinity. Okay, I will try to find omega. Okay, right, the formula, as I stated last time, is okay. So this, of course, in any case, it's a function. And in fact, it's a positive definite function of the implicit group. Okay, so evaluated at the element sigma of the here sigma is like sigma at infinity. Like that, it's given like this. Here, okay, it's here the notation is the following. So sigma is in S infinity, okay, with cycle structure. 2 to the M2, 3 to the M3, 4 to the M4. Okay, right. So right, I've already explained what it means, okay, before, okay, but just to recall, okay. So as we have said last time, so the set of conjugacy class of the group S infinity are parameterized by partitions rho without one, okay, right? So of course, I mean, so it just means it's if you like, it's just a finite Young diagram where no rho being equal to one, okay, right? So therefore, the notation here means that so in this partition, the 2 occur M2 number of times, 3 occur M3 number of times, 4 occur M4 number of times. Okay, right? So therefore, in this formula, right, you see, okay, so corresponding to say each value of k, okay, and if k occur in this partition mk number of times, then you take this expression and then to the mk power, and then take the product. Okay, so of course this is a finite product because mk is 0 when k is large enough, right? Because this is a finite Young diagram, right? So I mean, although we write it in this way, mk is 0 when k large enough. So therefore, this is in fact a finite product. Yeah. So and in fact, as I myself am not familiar with this type of terminology, but this is actually called some kind of supersymmetric. The reason I will perhaps be a bit clear later, but for the moment, okay, this sign might look strange. Okay, the occurrence of this sign -1 to the k minus 1 strange, but actually it is called supersymmetric Newton parsecs. Okay, so they need that like, so somehow when you switch the alpha i's and beta I, you incur a sign. Okay, this sign is in physics they usually refer to as a kind of supersymmetry. Okay. All right, and in that case, that's also the reason for motivating this definition. Okay, defining this algebra homomorphism from sim to the to this algebra. So this is this proposition that we want to prove. Okay, so now let's prove it. Proof actually is not difficult at all. Okay, so right. So the unique. So first part, the uniqueness is evidence. So uniqueness is evidence because we know that state as an algebra is generated by these generated as a polynomial algebra by these Newton power sums. Okay, right. So uniqueness is clear. Okay, and for the existence, means uniqueness of the method. While for the existence, okay, right, existence, right, again, because these are algebraically independent, because we know that these elements are algebraically independent. So it's so sim is just freely generated by these elements. Okay, so therefore, you certainly can define this as long as you can show that these guys are indeed continuous functions on the way. Okay, so we only need to show that the expressions for these continuous functions of omega. Okay. Maybe these expressions. Okay. Okay. Are continuous functions. Okay, right. But this is easy. Okay, so we just need a little bit of analysis. Okay, right. So indeed, okay. So for again for an element little omega in the Thomas simplex. Okay, with the alpha i's and beta i's being the coordinates. Okay, so by definition. Right, since alpha 1, right, bigger than or equal to alpha second. Okay. Of course, these things are between 0 and 1, okay, and sigma of alpha I, well, in particular, let's say equal to sigma of alpha I plus beta. I think the condition that all this is less than or equal to 1. So this certainly implies that for any I, for any index n, okay. So n times alpha n will certainly less than or equal to some I from 1 to alpha. Yeah, because this is say decreasing sequence. Okay, so certainly in particular less than this. Okay, it's of course. Okay, right. So therefore, alpha n is bounded by 1 over n for all n. Okay. And hence, n for n of course similar. Okay, similarly for the beta coordinates, similar to beta n. Beta n is less than n over n. Okay, right. So hence this implies thus for k an integer that is at least 2. Well, the series sigma alpha I k plus this converges uniformly. Okay, right, just the usual estimates, right? So you take the absolute value, right? You just use a triangle. Okay, since you take absolute value, so you only need to transfer this. Okay, so and using the bar, using these bar. Okay, so therefore let's say 2 sigma 1 over I in. Okay, so therefore, and as k is at least 2, so this converges. Okay, so therefore this series converges uniformly, and of course, the summand is a continuous function. Okay, on omega. So and hence by uniform convergence, this defines a continuous function of. So notice that this is also this fails in case 1, okay? Because in case 1, you cannot argue, right? The uniform convergence, right? Because in case 1, this is a harmonic series which diverges, okay? And indeed, as I have told you, when case 1, right, the function is not continuous, okay? So for integer k starting from 2, so the function send to this series is a continuous function on omega. It's a continuous function. Alright, okay, yeah. So as I said, the remark is that for k is 1, so namely the function sending omega to some of the parameters. So last time, this is not continuous, but only lower semi continuous. That's also partly explain why we have we separately define this PK, okay? The image of PK. So namely, if k is 1, okay, so right, if k is 1, then we just this is okay, as I said. So PK not omega is this series if k is at least 2. Okay, so if k is at least 2, but when the index k is 1, then we define it as just a constant function. Okay. Okay, so the reason I hinted last time, so namely that maybe let me write. Okay, the reason, as I kind of hinted last time, so is we define omega naught to be a subset of the Thomas sequence. Okay, so consists of those parameters omega with coordinates alpha and beta such that the sum of the coordinates is equal to 1. Okay, equal to 4. Right. Then omega naught is actually dense, you know. Okay, this is something that you can check. Okay, a little bit tedious, but not difficult. Okay. So in any case, so therefore, if you want to therefore you see that right, if you want to make sense of this situation with k is 1, well, okay, this expression is constantly equal to 1 on omega naught. Okay, so therefore, right, if you want it to be a continuous function, okay, then it will only be the constant function because omega naught is x. So that's why the algebra homomorphism is defined this way. Okay, so this algebra homomorphism from C to C omega, right, is defined in this. That's why we define this. Okay, yeah. So that explains this. This might look strange, right? And the reason. All right. Okay. So anyway, so this is part 1. Okay. So we just define this algebra homomorphism as you see. Okay. So yeah. So the key point is only to make sure that these things are indeed continuous functions. Okay. So for part 2, is to show that the image of state C omega is x in the supernorm function of C omega. Okay, right. So for this, we use the classic result, Stone-Weierstrass theorem. Okay. Okay, so for this, we use the Stone-Weierstrass theorem. So Q Stone-Weierstrass theorem. Okay, just recall the statement. Okay, so let's take what the general form. We only need the case for metric space, actually omega. So general form. Let X be a Hausdorff compact Blattl space. Okay, C omega, C of X. Algebra of real valued continuous functions. X, okay, also with the subnorm. The subnorm is a finite algebra, and A is a closed algebra. Say closed, of course, means respect to the subnorm topology of C of X. Okay, A is a closed subalgebra. That separates points. That separates points. Is okay, what does it mean? So, i.e., so if you have 2 points, let's say x and y, so x and y, okay, then this is an let's say G, okay, in the algebra in A, such that the value of G at X and Y are different. Okay, that's what I mean by separate point. Okay. Okay, furthermore, assume that the constant function 1 is in. Okay, then the conclusion is that A is the whole thing. A is the whole thing. Okay, so that is the Stone-Weierstrass theorem. So we of course apply to our setting. So we apply to the setting where it's not significant, and is the closure of the image of state in COP. Okay, so from the way it is defined, right? So we only need to show that this condition of point separation is satisfied. Okay, right? So we only need to show point separation. Okay, amount to the following. So to show that the values Pk not omega, the set of values, Pk not omega, okay, for all k uniquely determines omega. Okay, right. So point separation amounts to this assertion. Okay, and then the rest is obvious. Okay, so therefore the assertion. So you want to prove that the image of sim is dense. Okay, so you need to do this assertion. There are actually two ways to do it. Give one proof. Okay, so okay, so this follows this one proof. Okay, direct proof is this follows from the identity. So here below, so U is a complex variable. Okay, so okay, so here gamma is this constant gamma. So this kind is defined before. So the gamma is 1 minus the sum of the coordinates. Okay. Okay, so this of course is I defined previously, basically this super symmetric Newton mainly is these two constant function one. Okay. This is right. So this is an identity. Now we are not working. We're working with it as an identity of meromorphic functions. Identity of meromorphic functions, not just as a formal parsing. Meromorphic function on C. Right. Right. So, and of course, this you can easily verify. You essentially just use the geometric series, okay, to see this. Okay, yeah, it's a calculation that I leave it to you. Okay, so therefore, right. So given these values, right. So these are supersymmetric Newton sums. Okay, then it uniquely determines the right hand side. Okay, but the alpha i's and beta i's, okay, or more precisely, minus of beta I exactly occurs as the poles of these, right, of these functions, right? So therefore, they're uniquely determined by these supersymmetric Newton class sums. Okay, so that's the alpha base and minus beta and minus beta I are true. residuals. Okay, of this meromorphic function, or of the meromorphic function on the left hand side. Okay, of this meromorphic function. And of course, we do allow repetition, right? So we do allow, say, it could happen that say alpha 1 equal to alpha 2 equal to alpha 3, and then bigger than say alpha 4. Okay? You can read off the number of times it occurred also by reading from the residues. Okay, yeah, right. And the residues, and the number of repetitions. Will also read off from the residues. Okay, yeah. So therefore, the conclusion is that because this meromorphic function, if you look at the left-hand side, right, this meromorphic function is of course entirely determined by these values, right, the supersymmetric Newton sums. But because you have this identical meromorphic function, so therefore the alpha i's and the minus beta i's can be read off from as the poles, and also you can read off the number of repetition from the residue. So therefore, these alpha i's and the beta i's are uniquely determined by these supersymmetric Newton sums. Okay, so conclusions. So the alpha i's and the beta i's are uniquely determined. So including the repetitions. Okay. Next. The repetitions. Uniquely by these aspects of supersymmetric. Okay, so this is the point separation point. Okay. All right. So to just conclude the proof of this proposition. So the final part is also easy. Okay. Final part is the assertion. And, so now, okay, we are now constructing this algebra homomorphism from sim to the set of continuous functions of omega. Okay. All right, so we want to show that the kernel, is the principal ideal of sim. Generated P1 minus 1. Okay. So now clearly, right, any element in the principal ideal generated by this element, right, P1 minus 1 is in the kernel, because by the very construction of this algebra homomorphism, the element P1 is sent to the constant function 1, right? So, and therefore, any element in here, of course, it becomes the zero function on omega, okay? And conversely, okay, so clearly, okay, so P1 is 1 sets to the zero function. Beta Okay, so this is clear. So conversely, or to show that this is exactly the kernel. Okay, so now if you have a f in C, that is the kernel. Okay, so we can always write f from write f. As an expression, so let's say f prime. So f prime is of course an element in C that does not involve P1, does not have P1 the expression. Okay, and plus principal line with this guy. Okay, you can certainly always do this. Okay. Okay, however, of course, you need to show that this f prime can only be zero. Okay, so in other words, so we are reduced to showing the following. Okay, so now rewriting this f prime. So if f is an element in C that is generated by generated by these pk's, okay, with k starting from 2. Okay, so namely it does not involve p1. If f is here such that the image in C omega is 0, okay, then f is in omega. Okay. So you're reduced to showing this. Okay, but this is also clear because if you simply so this is clear. By evaluating the points. These points omega. Okay, so namely that evaluating at those points where the beta I coordinates are just 0. Okay, then the PK not okay evaluated at these points are just the usual Newton power sums. Just the usual, usual Newton power sums. Okay, and we already know that the Newton power sums are algebraically independent. Okay, and since we know that Newton power sums have independent. If such an expression, okay, right? If you have a f in here, okay, whose image in C omega, namely this f naught is the identity zero function of omega. In other words, you basically this means that you evaluate, okay, you really evaluating these pk's as functions, okay, and also they becomes the usual Newton power sums anyway. Okay, now, but as I've said, okay, we already know that the Newton power sums are algebraically independent. Okay, so if upon evaluation, it becomes the identity zero function. Okay, this I think zero function. Then this f okay can only be zero. Okay, so okay, so this is essentially this is the proof. Okay. So yeah, okay. So maybe this completes the function. But let's take a break first, okay, and then I will give you another proof of the point separation property. Okay, let's take a break. Yeah. Yeah. Let's see whether maybe the fan. Let's see. Oh, the fan is already at max.
Whatever. If they don't turn the AC off, we cannot do anything.
Okay. So all right, okay. So let me give another proof of this point separation property, which is probably a little bit more illuminating. Okay, let's see. So, another proof of the point separation. Okay, yeah. So again, so for any omega in the Thomas select, okay, so as usual, if alpha i's and beta i's being the coordinates. So let us define the measure nu omega on the intervals. Sorry, minus 1 to 1 by the following expression: nu omega being equal to sigma alpha I delta alpha I. Okay, and then plus sigma beta I delta of minus beta I minus 1 plus gamma delta 0. Okay, so here as before, gamma is 1 minus sum of the alpha. Okay, yeah, so of course the delta is the usual Dirac delta. Okay, so delta x is the Dirac delta from delta x. Okay. All right, okay, so you see that nu omega is a problem measure. So that just means that nu omega of the, I mean, if you integrate the whole space into okay, right, that is exactly the way you define, okay? Of course, each of the alpha i's, right, recall that each of these alpha i's are between 0 and 1. So therefore, the measure, of course, is supported on the interval minus 1 and 1, okay? Yeah. And the definition of gamma being 1 minus sum of these things, of course, ensures that when you sum over all the weights, okay? So basically, these are just a Dirac delta with the corresponding weights, right? Alpha I, beta I, and Z and gamma. When you sum over these, it is just 1. Okay? Yeah. Okay, and of course, a gamma is also between 0 and 1. Condition in force on the in the definition of the Thomas sequence. Okay, so this number is also between 0 and 1. Okay, so therefore this is indeed a problem measure. Okay, yeah. Right. All right. Okay. So now we compute the moments of these measures. You so this is the way the probabilities write research. Okay. So now if you make this computation and computation that I leave it to you. Okay. So here k is any integer. Okay. K is any yeah, k yeah, k is just any non-negative integer. Okay, yeah. Then well, okay, so this is exactly this okay, maybe yeah. So let us first consider this. Okay, k is a starting from 1. Okay. Of course, if k is 0, then it's just this case. Right? So then if you come to the moment, this is exactly this. Okay, yeah. Yeah. So because k is positive, okay, so therefore this final term does not show up, okay, because it's Dirac delta at 0. Okay, so therefore this final term doesn't show. Okay, and so you got this. Okay, so therefore so in other words, rewriting this formula, we got the following. So the moment of this measure mu omega. Okay. Well, this is equal to yeah. In any case, this is k plus 1 not omega and positive integer k. Non-negative integer k. Okay, yeah. Right, because if k is 0, right, then we define this also we define this to be identically equal to 1, right? When k is 0, okay. So it matches with this thing because we have defined this to be identical. While if k is positive, right, then this index is at least 2, and we define it to be this. Okay. So now, consequently, if say if omega can say omega prime in the Thomas simplex such that well, okay, pk naught of omega is equal to pk naught of omega prime for all values of k. In particular, then we have okay. So then that will imply that this the moments are equal for all right? For all positive integers. Sorry, for all non-negative integers. Which implies that the integral of these two measures against any polynomials are equal. Okay? Bigger. For any polynomial x. then the original Weierstrass approximation theorem. Okay, so this implied by the original Weierstrass approximation theorem. Okay, so they need that any continuous function can be uniformly approximated by polynomial. So therefore, right, this statement, I leave it at you to it as an exercise. Okay, by using the original Weierstrass approximation theorem, that implies that any continuous function f, when integrated against mu omega, is equal to the corresponding integrated against mu omega. For any continuous function. Okay, yeah. Okay, but this is enough to conclude. So this included the two measures. So this is a basic measure theory. Okay, if you like, you can see. Okay, so right, two measures when integrated against a continuous function. Okay, for us these are complex space. Okay, so if the integrals are always equal, then the measures must be equal. Okay, but from the way we define the measures, right? Because the measure clearly, okay, captures the coordinates of the Thoma parameter, right? So the measure clearly determines the coordinate. Similarly for so if the two measures are equal, this implies that the omega is equal. Okay, so this is another proof of the point separation property. And as you see, okay, perhaps this also a more natural way to see why this supersymmetric Newton sum shows up. Okay, so because it's quite natural to define this measure. Okay, and then the moments of these measures are exactly these values, these supersymmetric Newton. Okay. All right. Okay. So anyway, so this is the proof. So now we can proceed to justifying some of the formulas that I have shown you previously. Let's see. Okay. Yeah. Let me. Okay. So in a case, to sum up, so we have defined this algebra of the orbital. So this is a algebra of the orbital. Okay, so it is defined by requiring that Tk being sent to this supersymmetric function, okay, supersymmetric Newton sum when the index k is at least 2, okay. And it's just a constant function 1. Then k is 1. Okay. Yeah. So now let us compute the image of other elements. Okay. So for instance, say remember, right, in this theory, besides the Newton power sum, we have the other important important symmetric functions, right? Like the elementary symmetric functions or the complete homogeneous symmetric function, and of course also the Schur function. So let's compute, okay, what the image are, okay, or at least give the formulas for these functions. Okay. Okay, so first rho is a condition. Okay, so as usual, rho being rho coordinates. Okay, in this form. Okay, so these are the rho in the usual rho coordinates. Okay. So these are integers, okay, and L is the length of the path. Okay, then rho. Okay, remember P rho we define it to be just the product, right? Okay, so then from the original way we define P rho, it's just the product of these Newton power sums with index. Just okay. P of okay. The index is 2. P rho 1, okay, and times dot up to P rho, okay. Right, it's not. Okay, right. So this is the original way we extend these Newton power sums, okay, to right. Originally, these Newton power sums are defined for index k. Okay, k is any positive integer, and then say we extend the definition by multiplicativity. Okay, so in other words, if rho is a partition, so therefore each of these is in the usual rho way of writing it as in terms of rho coordinates. So these are just positive integers, okay, and rho 1 bigger than or equal to rho 2, bigger than the etc. up to rho L, okay, and the L being the length of the partition, right? Then the Newton power sum respect to rho is just the product of these Newton power sums with indexes rho 1, rho 2, up to rho L. Okay, so therefore, as this right is this map is an algebra homomorphism. So therefore, you just the image, right? Just the product of these things. Okay, and we know how to compute these. Okay, the definition is this thing. Okay, so therefore, this is easy. Okay, just by multiplicativity. Okay, now as for the complete homogeneous symmetric functions and elementary symmetric functions. Okay, we first or we again use the generating function. Okay, so recall that the generating function for the Newton power sum, okay, is is defined by this. Here case okay, so and hence, under this algebra homomorphism, so which I just put a knot to denote the evaluation of every terms under this algebra homomorphism. Okay. So this is sum A from T A not T A. Okay, so and let's say so again, so or maybe again it's before let us evaluate it and change common parameters omega. Okay, so therefore this is equal to now right again we have to consider the case where k is 1 or bigger than 1 because when k is 1 this is P, this is identically 1, okay? So therefore, for k is 1, the term is just t, okay? And for k is 2. Okay, this is the supersymmetric problem. Okay, yeah. Okay, so you just evaluate the formulas I have given. Okay, so this function being evaluated at any little omega in the Thomas simplex. Okay. And then let's do a little bit of series manipulation. I just give you the formula, then you got this. Okay, where of course as before, again as before, gamma is not. Okay. Yeah. All right. Okay. So now we can give the formula for at least from the generating function for these formulas. Okay. So being the generating function for the complete homogeneous symmetric function. Okay. So we have seen before that is equal to the exponential of the generating function for the Newton power sum. Okay, so and hence if you with again putting a knot to denote everything, the result of making this evaluation of the algebra homomorphism, in other words, h naught t being some h any naught t thing, evaluating every term under this algebra homomorphism, then this relation is equal to exponential of p naught t. But we have already evaluated p naught t. Okay, so therefore making a substitution. Okay, so making the substitution. gives the formula for the generating series. Okay, for this generating series, namely equal to this. Yeah. So exactly this generating series. So yeah, unfortunately, I can't write the explicit form for these things. Okay. So, but it's common in combinatorics, right? So a lot of times you can, you might not be able to write down the formula, okay, for each term, but somehow, okay, for the generating series, you can at least write down explicit expression. Right, and of course, the same thing goes for the elementary symmetric functions. Okay, so similarly, for the elementary symmetric functions. Okay. So the generating function for the E case, the elementary symmetric functions. Okay. We have seen that the identity between the generating function for the complete homogeneous symmetric function and the generating function for the elementary symmetric function, namely h or right, et is equal to a minus t and oops. Okay. This is something we've seen before. Okay. And so again the same thing. We not t denoting every term being evaluated with respect to this we have this relation again being preserved. Okay, yeah. But we have already evaluated this. Okay, so just making a substitution. All right, so note that so here that it is affected by interchange of alpha I and beta. Okay, right. So in other words, although okay, you deduce the formulas in the end, okay, it has this, but comparing these two, right, you see that this one is obtained from this one simply by switching the alpha i's to beta. All right. Okay. So as an example, these are give you some computations. So example. Let's consider the Hom parameter where all the alpha i's and beta i's are just zero. Okay? Yeah. So i.e. alpha I, beta I. So in this case, gamma is 1 because gamma is 1 minus the sum of these parameters alpha and beta i's. So if alpha i's and beta I are 0, then gamma is 1. Okay, so as the generating function for both the generating function h naught t and also the generating function t Okay, so i.e., so therefore k not evaluated at this point. Okay. That's one over k factorial, like the I mean the Taylor series for exponential. Okay. All right. Okay, so finally, for the Schur function, okay, so finally, Schur function. Okay, so here we have lambda is any finite time. Okay, so there are two ways to compute it. So either you use the Jacobi, so use the Jacobi Freudian identity. Okay, so this is formula I have also given before, but now here's a justification. Okay, so because so for any larger than or equal to length of the partition, we know that Jacobi Freudian identity. So it's a determinant of this matrix, okay, and this matrix, okay, is with in terms of these complete homogeneous symmetric functions with indexes given by these numbers, okay, lambda I minus I plus j. Lambda i's are of course the row coordinates of lambda, okay, and as before, okay, this is in the entry is interpreted as 0 if this index is negative. Okay, yeah. So you have this Jacobi Freudian identity, okay? But this map, the map is an algebra of models, right? The map that we have defined. This is an algebra of models. So therefore you can put a norm on everything, okay? Because it's an algebra of models. And since we already know, in principle, right, we already know at least at the level of generating function. We already know these things. Okay, and at least the generating function. This also allows us, okay, in principle, to compute this. Okay. Okay, actually, I should not erase by this. Okay, so again, as an example, let's again take omega to be the where all the parameters alpha I and beta I and 0. Okay, so as we have seen, hk is not evaluated at this common parameter, right? This is equal to 1 over k factorial non-negative k. Okay, and hence lambda. So I got hence or any condition lambda not evaluated at this point. Well, okay, so by Jacobi Freudian identity, together with this formula, okay, namely the hk naught evaluated at this point is 1 over k factorial. So therefore this is equal to the determinant of this matrix with the following entry: 1 over lambda I minus j. Okay, so here I take as before, just take any integer larger than or equal to length partition. Okay. Now, but we have, I have actually told you this before, okay. I will prove it later, okay. So, in fact, we prove a more general formula, okay. But I tell you at the very beginning, this is equal to actually dimension number of box of lambda factorial. Okay, this again, this is for the Frobenius form for the dimension. Okay, what's this? Okay, so in particular, once again you see the measure coming up. So dimension of lambda is this quantity. Right, because of this, so it's equal to the number of box of lambda. Okay, and this is exactly the Poynter that we have seen before. Okay, so yeah, so somehow this Poynter in the classification of extreme carriers given by Thomas theorem. Okay, the Poynter measure corresponds to the case when the parameter omega is this point, okay, where all the coordinates are zero. Okay. And then the other values, okay, in a sense, okay, is almost like a deformation of the Poynter measure. Okay, so giving, yeah, okay. Roughly speaking, I mean, I think it's fair to say it's similar to Nadia may not agree, but it's like a continuous, like a principal series, so to speak. Okay, because you see that, right? Omega, right? So it's like a continuous family. So again, from the representation theory point of view, it's very interesting because when you look at the finite symmetric group, right, then of course you only have finite many irreducible representation. It looks like everything is a discrete series, so to speak. Okay, but when you look at S infinity, then it's like everything becomes continuous back. Okay, it's like the principal series, so to speak. Okay, yeah. So yeah, it's almost like that the discrete spectrum become packed together so that in the limit they form a continuous series, so to speak. Okay. Yeah. Okay.
So far, you never had any representation.
No. Yeah, exactly. So because as I said, okay, last time, so for representation theory, to do it properly, you really need the Gelfand pairs. Okay. So you really need to work with the Gelfand pair with G being the model as infinite and then the characters really occur as you mentioned before as the diagonal matrix coefficients. Yeah. The character show up as a diagonal matrix coefficients for this Gelfand. Okay. But it takes some work, so therefore I will
The representations occur as subspaces of N2 of G over K, something like this? Or?
Okay. So you can construct a analog of the regular representation, but you need some work. Okay, so because the obvious choice is not the correct one. Okay, because you see, you need to put a measure, right? Now, S infinity just a discrete countable decision. So if you do the obvious thing, namely just the counting measure, then this is not the correct one. Well, okay, so this is not the thing you would find interesting. Okay, so in fact, this is the this is actually irreducible. Okay, and in fact, it corresponds exactly to the character of this is exactly the Panchero measure. Actually, I mean, yeah. So therefore, what you want to do it. So oh, sorry. Okay, yeah. I mean. Yeah, I mean. So the usual thing, one copy on acting on the right, the other copy acting on the right. Okay. So if you really want to do the representativity, you need to work with a certain inverse limits. Okay, not the natural inductive limit. Now, of course, this is a slightly strange thing. It's certainly not a group homomorphism. So there is a natural projection map going the other way around. Okay, it's not a group homomorphism. Okay, but it does respect the group action of Sn on the left. I mean on the right and the left. Okay, so there's a certain inverse limit that you can construct, and the point is that this is kind of like a compactification of S infinity. Okay, so S infinity itself is a countable discrete group. Okay, so there's no natural measure you can put on other than the counting measure. But this is different. This is a projective limit, a kind of like a compactification. So there's a natural measure, some measure you can put on. Okay, and then with this, then you can define this natural group action. This okay, and the spectral decomposition give you a very interesting measure on the Thomas simplex, and it is also this measure that is used in a lot of those probabilistic models. Okay, so but anyway, so if you want to construct a natural version of the regular representation, it does take more work. Okay, so which is a different story. Okay. So therefore, for this course, I concentrate on the characters. Okay. All right. Okay. As I said. Okay. So therefore, you see, right? So these formulas are shown up. Okay. And okay. So let's see. Okay. So I think I have the time for stating the main theorem. Yeah, I erased this one. Okay, so just to state it more formally, okay, integral representation of coherent systems. Of distributions on Young graph. Okay, so once again, recall this notion which we have already defined. So a coherent system of distribution on a Young graph. Okay, so each Mn is a covariant distribution on the n level of the Young graph, okay, which is just the set of all Young diagrams with n boxes. Okay, so therefore Mn, so it's just an assignment of a non-negative number to each Young diagram with n boxes, such that the sum of these distributions, okay, is equal to 1. Okay, right. So you have that so you have such a number, n lambda, which is not negative, for n lambda, 1 n, such that the sum, when you sum over these lambdas, just one distribution is okay. And of course, coherence, as I've said before, coherence means that when you have from the nth level to the n minus 1th level, then you have this coherency condition. And for all n, all mu this one, then we have the coherency condition. Okay, so n evaluated at mu is equal to this weight. Here, let us sum over with lambda being obtained from mu by adding points. Okay. Alright, so this is a coherency condition. Okay, so recall that we have seen one example of such thing, okay? Namely the Plancherel measure. So recall the Plancherel measure, the basic example. The coherent systems given by the Plancherel measures. So mainly m and lambda equal to exactly this expression. Lambda squared so yeah, I've shown you before that the coherence condition exactly is deduced from the branching rule. Okay, so the branching rule exactly allows you to show that these Plancherel measures for different ends are indeed coherent. Okay, now other than the Plancherel measure, as I said, it's not that easy to write down these things because you see, right? So while this is a kind of like algebraic condition, okay, but this kind non-negativity is not easy to show by directly. Okay, so this is a kind of requirement, like because it has to be a probability distribution. So in particular, these numbers has to be okay. So right, so that's not easy. It seems to be easy to write down such things just by hand. Okay, so but in any case, so this main theorem is to give an integral representation of these objects. Okay. All right. Okay. So, of course, this is the main theorem. Okay, that we are going to prove, which in particular implies Thomas theorem. That's going to see. So there's a objective for example. Between these coherent system distributions on the Young graph and probability measures on Thomas simplex. Okay, so this is the probability on Thomas simplex. This is before. Which is determined of such things. Yeah, okay, let me. Yeah, okay, I write. Okay, such that the following holds. Okay, so namely, if P is as I said last time, so P is like giving the Poisson integral form. Okay, so such that n lambda equal to lambda times Okay, yeah. Or n. Or okay. So here, this is what I have defined before. Okay, so this is yeah. Okay, yeah. So yeah. So you know this S lambda thing. So this is the image. The algebra from the models. Okay, from same to B omega. Okay, so in particular, this guy is a continuous function on omega. So in particular, certainly is a measurable function. So therefore, we can integrate this back to this P. Okay. So in other words, yeah. So you give it, as I've said, okay, give a complete classification of these coherent system of distribution of Young graph by problem measures P on the Thomas series. So in particular, the delta measure, okay, delta measure of omega correspond to the extreme elements. Yeah. Okay, once again, okay, objects on the left hand side and the right hand side form a convex set, right? So this is a bijective correspondence preserving convex functions. Okay, so the set of problem measures on omega is a convex set, okay, while the set of all coherent system of distribution on the Young graph is also a convex set. Okay, and this bijective correspondence preserve the convex structures. And the extreme, so the extreme elements. So the extreme elements in the space of problem measures of omega, the extreme points of extreme elements in the space of problem measures on omega. Well, exactly the Dirac delta measure. Okay. Exactly. The Dirac delta. Okay, so delta omega. So correspondingly, so these then correspond to well, because this bijection preserves the convex structure, so therefore, if it's an extreme element in here, okay, then the corresponding coherent system of distribution is also an extreme element here. So, by definition, so we define the extreme coherent system of distribution. On the Young graph. Okay, so okay, so in other words, MA. So note it. Okay. So this is a Dirac delta measure on omega, little omega, okay. But when you look at this formula, it just means that, well, okay, for a value of little omega, okay, you just evaluate the integral at that little omega, okay, right? Because it's a delta measure. So therefore, it just means, so i.e. so from the integral formula. So the formula for these extreme system of distributions is simply this, okay? So any omega divided any Young diagram lambda and box is equal to function of lambda times this lambda not means for any Young diagram. Okay. So as I've said, right? So example, omega is the point where all the coordinates are 0. Then, as we have seen, this number is equal to dimension lambda divided by n vector. Okay. So here lambda being is a Young diagram. Okay, so then this number is exactly the formula for the tangent measure. Okay, so okay, and that's a reason for my remark previously. So namely that with omega being the point where all the coordinate are 0, so okay, so this gives the tangent measure. Okay, yeah, for all the levels. Okay, so therefore when omega is other points in the Thomas simplex, you can think of it as a kind of deformation of the tangent measure, so to speak. Okay. So here there's actually a non-trivial point here, namely that it's not entirely obvious that this value is not negative. Okay, yeah. So but we'll show it later. Okay. All right. Okay. So, okay. So let's see. Okay. My time is all basically up, but maybe let me just say a few words, okay, and then continue on next Tuesday. Okay. So yeah, okay. So this is actually equivalent to the result that I've stated last time. Okay, so and in any case it's a simple computation. I will show it next week. So this is equivalent to the theorem that we have stated before. So the integral representation of parameters of f. Okay, so namely that the theorem is that there is a bijective correspondence okay, this bijective correspondence actually preserve complex functions. So between times across normalized character of oxygen in the sense that we have defined before, while P is again a measure data. Okay, yeah. Determined by such that I sigma equal to of P rho. Okay. P. Okay. For any sigma x to infinity, and this rho being the cycle structure of C. Okay, so in the sense that I have defined for you before. Okay, so namely that, as I've said, okay, for any element sigma S infinity, the conjugacy class is classified by a partition, okay, where with no parts equal to 1, okay, and denoting this partition by rho, okay. Then P rho, okay, again I just defined before, okay, so this you just yeah, I mean the generalize, okay, so when you say, as I say, you say rho is a rho, I mean in terms of it's a partition, so you the rho coordinate is rho 1, rho 2 up to rho L, and P rho is just the okay, yeah. So each of these cells is just like supersymmetric Newton sums. Okay, right. So this is the integral representation for characters. Okay? And in particular, is okay with little omega in the common syntax, right? Then high omega is the form of top that I have okay, as you see. Okay. So right, so the Vershik and Karol basically generalize the original theorem of Thoma in the form of an integral representation. Okay, so all from this perspective, the original form of Thoma corresponds to the case when the measure P is just a Dirac delta measure. Okay, on the matrix. Okay, and of course these two results. Okay, this result and this result are equivalent. Okay. Yeah, maybe this result and this result. The relation next Tuesday. Okay, so these are equivalent to equivalent. By using as given by using. Okay, so namely that, as I've said before, okay, so for any character chi is a character it's a character on S infinity. On S infinity. Then if you restrict to Sn, okay, right, then you can expand it in terms of the normalized character of Sn, which, as I said, okay, we know parameterized by Young diagram with n boxes, and then these coefficients, okay, exactly correspond to these. Okay. So that's how the way you pass between character and these coherent system distributions. And under this correspondence, these two integral representations exactly correspond to one. So, and hence in the Vershik-Karol approach, so again, this is something that I mentioned, I think last time. So, in a way, in the proof, you practically forget everything about the symmetric group and work entirely with this level, with this coherent system of distribution, which concerns only this Young graph. Okay, but of course, the Young graph already packaged all the crucial representative theoretic information, namely the branching. Okay, so therefore, although you forget the symmetric group, okay, but the essential information is here. Okay, in the form of the Young graph, or more properly speaking, so this system of distributions, coherent system of distribution. Yeah. Okay. So and you and as I say you are working with this object. Okay. Yeah. So yeah. Okay. And let's continue next Tuesday. But we essentially we are most important points. Okay. Yeah. So we continue next Tuesday.
人类的这个，跟这个妹子天地阳光。啊，我觉得那个是保育，过去。
就是如果你打到质的22元，你不用说对。但没有质检资料。